Good evening, students. Welcome to one more session of your WOC, that is your World of Chemistry. So World of Chemistry basically is a channel which is established for grade 10, 11, 12 as well as JEE as well as NEET also, right? So recently in the community tab I've asked which topic should I do next, correct? So most of them said you wanted organic reaction maps, so mind maps rather. So I have decided to do the organic mind map including all the chapters. So this is what I have written. See here, you're able to see this full organic chemistry mind map. This will cover everything. So please I request you all to take one how do you say, an A3 size paper, prepare this mind map and keep it on, stick it in your study table. Now let us start with the first topic. Carefully note everything and see that if you're not understanding anything, try to put it in the community tab, right? Put it in the comment section, right? So we have studied basically alkenes, isn't it? We started with the alkenes topic in grade 11th. The organic chemistry starts with hydrocarbons, that is alkanes, alkenes and alkynes, and then gradually we go. Let's see. So here I have taken the chart paper so that it is easy for me to fill completely for you all, right? So here let me take out the caps. Okay, now let's start. So first of all, whenever we speak about alkenes, now let me first write that. We'll start this now. Here I'm going to take an alkane. Okay, done, right? Alkanes are there. Let me take an example of ethane, right? So this is your ethane. So what happens, first step, suppose if I have to convert alkanes to your alkenes. So I'm going to convert alkanes to alkenes. How can I convert alkenes to alkenes? So basically the alkene which I'm going to form is ethene. Now ethane, this is ethene, right? So here I can use a process called cracking. Okay, I can use a process called cracking with which one? With aluminium oxide and SiO2 also. What temperature? At 450 degrees centigrade I can use this and convert it. This is fine, right students? Yes. Now to convert alkenes back to alkenes means if I have to convert it, just see here the reverse. Oh, right. So here what process you're going to do? Here we are going to use a process called that is you're going to break this double bond and convert or add hydrogen. So addition of hydrogen is nothing but reduction, isn't it? So which one, how do you add? I'm going to use add hydrogen in the presence of metal catalyst nickel, or I can use hydrogen in the catalyst with platinum. This is also fine. This is over. So alkenes to alkenes is over. Alkenes to alkenes is over. Right. Now further, suppose if I have to further convert, I can convert alkanes to alkyl halides. So this is your grade 12th, isn't it? So how can I convert alkanes to alkyl halides? So basically your alkyl halide, what is the formula? Let us write there. Alkyl halide, this is your grade 12th, that is your CH3 CH2Cl. How can I convert alkenes to alkyl halide? I can use something called FRS. What is FRS? I can use something called free radical substitution reaction. FRS stands for free radical substitution reaction. What is required here? I am going to take chlorine in the presence of ultraviolet light. This is fine. This is over. Okay, done. Now gradually let us proceed further. Further, if I have to convert alkenes to primary alcohols, how can I convert? I can convert alkenes to primary alcohols. Okay, so primary alcohols, what alcohol you're converting or you're getting? Two carbons. So here also 2 carbons. So primary alcohol, how can I get? I can get alkenes to primary alcohols by a process called hydration, right? Or that is the method which we are going to use is EA. EA stands for electrophilic addition. I'm going to use electrophilic addition for converting. What am I going to use? I'm going to use phosphoric acid and hydrolyze it, H2O, and hydrolyze. Then double bond breaks and it forms primary alcohol. This is fine. Now suppose if I have to convert primary alcohols back to alkenes, how can I do that? I can convert primary alcohols means I have to remove this water molecule, means dehydrate this. If I remove the water molecule, OH from here and H from here. So for dehydrating, what going to use? You're going to use H2SO4 at what temperature? 180 degrees centigrade, or you can also use Al2O3 at or you can heat it and you will get that, right? So what is this process? This here, basically the process which is happening is capital E. What is capital E, students? It is elimination is happening. So we are going to do elimination here. This is fine? Yes. So this part is over. Now, what can I further convert it into? I have to convert further primary alcohols. Let us take this. What can I do? I can convert primary alcohols further into aldehydes. Okay. So I can convert primary alcohols into aldehydes. So 2 carbons are there. This also is 2 carbons. CHO. Okay. What is the process of converting primary alcohols into aldehydes? It's nothing but you can use, that is your oxidation, isn't it? You're going to add here, see here, you're going to remove one hydrogen, or removal of hydrogen or addition of oxygen. Here just see CH3 is here. I'm removing one hydrogen here, one hydrogen here. Okay, right? So I'm writing oxidation and distilling. You can also write reduction also here, no problem. Right, now suppose if I want to convert aldehydes back to primary alcohols, what should I do? To convert aldehydes to primary alcohols, simple, isn't it? So what should I do? I have to do reduction, addition process, done, and heat it. You will get it. Done, students? Okay. Now, further what can I do? I can further convert aldehydes to acids. So you can further convert aldehydes to acids, that is your carboxylic acids. So how many carbons are there? 2 carbons. So here you get 2 carbon acid, that is carboxylic acid. Done. Now, here, suppose if you want to convert acid back to aldehyde, what should you do? Here, first of all, aldehyde to acid, what is the procedure? Again, same oxidation process, and you heat it. Done. Suppose if you want to convert acid to aldehyde, reduction process, same thing. Yes, and you heat it. This is fine. See here. Here you are going to remove oxygen and add hydrogen. Simple, isn't it? So removal and add hydrogen. Just taking out oxygen here. Done. This is okay, students? Any doubt? Okay. Now here one more thing. Suppose if you're getting confused, oxidation in the forward direction, reduction in the backward direction, you can remember easy. Right. Further, if I have to convert acid further, so I can further convert this acid into one more compound, that is nothing but acid chloride or acyl chloride also, no problem. So I'm going to convert acid chloride or acyl chloride. How can I convert acid chloride or acyl chloride? I can use 3 important things, that is thionyl chloride is 1, or you can use PCl3, or you can use PCl5. All the 3 you can use to convert. Suppose if I want to convert acyl chloride back to acid, I want to convert acyl chloride back to acid. So what should I do? I will do a process called hydrolysis. So that is, we call it as HYD, that is hydration, nothing but addition of water. When I add water, I can get back the acid. So what is acyl chloride formula? We have not written here. That is nothing but CH3COCl. Till now this is clear, students. This is simple. Yes, all alkanes to alkenes, alkenes to alcohols, primary alcohols to aldehydes, aldehydes to acids, acids to acyl chlorides. This is over. Now little bit we will proceed. Now here primary alcohols are under oxidation, you get this, that's fine. Suppose if it is secondary alcohol, what happens? Tertiary alcohol, what happens? We'll do. Before going that, we will come back to again alkenes. Just see, let us see what are the different possibilities of alkenes. Let me turn the page and write it for you. Now, what do we have? Basically, we have alkenes. Let us put that alkenes in the center. Okay, alkenes. Right. So, alkenes, from where did I get alkenes? I got it by cracking process from alkenes, correct? Now, just see. We have different conversions here. We will take all the conversions and check. Now, first thing, suppose if I take the alkene and I'm going to introduce cold KMnO4 here, okay, under cold conditions, what is the process happening here? It is nothing but EA. What is EA? EA is nothing but electrophilic addition. So capital EA stands for electrophilic addition. So in electrophilic addition, what product do you get? You are going to break. Now here alkene is what? CH2, double bond CH2. So you are going to break this double bond here. Yeah, and this is an oxidizing agent, so you're going to break this double bond, and the product which we get is CH2, CH2, OH and OH. This is your diol, correct? Both hydroxyl groups are there. This is fine. Further, suppose if I take the same, like, you know, the alkene, the same alkene, and what am I going to do? I'm going to here do addition polymerization. Let us take that. I'm going to perform something called addition polymerization. When I do addition polymerization, as you know, the chain goes on extending, right? So the double bond breaks here, and what is it going to happen? Just see, this double bond breaks and it starts forming a polymer. How does it form? You're going to write, so C, now this double bond broke, C is single bond C, two hydrogens are there, one hydrogen above, one more hydrogen here, and this forms the polymer. This chain continues like this, isn't it? Right, so this is one case. Now, the same alkene, suppose if I am going to do, or if I take or perform a reaction, that is electrophilic addition reaction. What am I going to do? I'm going to take bromine in CCl4. So here the reaction happens in dark. Bromine in CCl4. When you do perform this in the dark, bromine in carbon tetrachloride, the product you get is vicinal halides. Vicinal on both the things. You'll be having on both the things, right? Both the carbons. Suppose if you perform, or if you take the same alkene and you are going to take bromine in aqueous solution, means bromine in aqueous solution, and again you are performing which type of reaction? Electrophilic addition only. But here you are going to perform this reaction at room temperature, the normal room temperature. What are you going to get here? Just see, students, here you are going to get two different products. What are the two products? One product would be vicinal halide, but at room temperature you're also going to get, remember, yes, we have seen, isn't it? Addition, Markovnikov addition, anti-Markovnikov addition also, right? This is symmetrical alkene, just say, right? So here this is one option. Now further, if I have to take, what else can I convert? The same alkene, if I take, suppose if I am introducing or HCl and I'm performing electrophilic addition, because double bond is there, it's addition only, correct? What is it going to form? This alkene, the double bond breaks and HCl adds, and you get haloalkenes. Haloalkenes you get. What are haloalkenes? This haloalkene, this is what you get. This is fine, students. Done? Okay. Now, I can, same haloalkane, if I have to convert back to alkene, what can I do? Same haloalkane, if I want to convert back to alkene, simple thing, I am going to use ethanol, or alcoholic KOH rather. So I'll be using ethanol in the presence of KOH, alcoholic KOH, and heat it. Here what happens? Elimination reaction happens. When elimination reaction happens, HCl goes out and alkene is back to its stage. This is fine. Yes. So one is the addition polymerization, one is the KMnO4, this part. One is formation of dihalide, here formation of two compounds, here the formation of haloalkane, and haloalkane back to it. This is fine. Okay, clear. Yes. Now we've stopped here, isn't it? Now we will take from here. I'll start again. Let me take a fresh page. Now where are we? We are at haloalkanes. Now what did we say? We said haloalkanes, basically what are we going to get? I have two methods to convert now. Here I said basically alkanes are getting converted to alkenes, correct? Alkenes are getting converted to primary alcohols. Now alkenes we have converted into, that is your haloalkane. This is where we have stopped, isn't it? We have stopped in the last page at this point. Now see here, I can convert primary alcohol, as I said, into haloalkanes. By which procedure? I said just recently also, I said I can use HCl, or I can use thionyl chloride, I can use PCl3, I can use PCl5 also. Then I can convert primary alcohols to alkyl halides, CH2Cl. This is fine. What is the primary alcohol here? CH3, CH2OH. This is fine, students. I think I have stopped here. Now see here, again if I have to convert haloalkanes to primary alcohols, what can I do? I can use a process called nucleophilic substitution reaction. NS stands for nucleophilic substitution. What am I going to use? I'm going to use aqueous sodium hydroxide here. Okay, so when I use aqueous sodium hydroxide and I take this nucleophilic substitution reaction, just see, simple, it gets converted to primary alcohols. This is fine. Okay, now further what can I do? This haloalkane, whatever is there, you know, this one, this part. Further important thing, just see, the same primary alcohol, suppose if I'm using KCN in ethanol, okay, in KCN I'm using in the presence of ethanol. Here what is the type of reaction? It's nothing but nucleophilic substitution reaction. Same thing, if I take the same haloalkane and I'm going to again do nucleophilic substitution only, but this time I'm going to use ammonia and heat it. Now see the products. If it is KCN here, the halide group is replaced and what do you get? You're going to get CH3CH2CN. Okay, you'll get nitrite. Now if I take the same ammonia, you're going to get amine, CH3CH2NH2. Cyanoethane or ethyl cyanide, or here it is amine, ethylamine. Both are fine? Yes. Now further, suppose if I take this ethylamine, I think it is the image is clear for you all. I'll push this paper a little bit. Okay, suppose if I take this ethyl cyanide, further if I have to convert, what can I do? I can take the same ethyl cyanide, I'll perform hydrolysis to this. When I perform hydrolysis, which in the presence of dilute HCl I can use, or sulfuric acid, and just warm it, rather heat it. What do you get? The cyanide group is replaced and you will get an acid, CH3CH2COH. Further, if I reduce this, I perform a process called reduction. What product do I get? I get amine, NH2. This is fine. Okay, so here what happened? Hydrogen is added to this carbon, one more hydrogen is added to this. So shall we put here 4, because 4 hydrogens we have added. So we have got an acid and we have got an amine. This is fine, students. Okay, gradually I'm going a little bit move further and further. Right, now this primary alcohol, this part is over. Now let's see, suppose to the same primary alcohol, suppose let us assume here I am introducing sodium metal. What do I get? Sodium metal. When you are adding metal to something, hydrogen gas is evolved, isn't it? So the hydrogen gas, whatever is there in this hydrogen gas comes out as half H2, and what is left? It is C2H5ONA, sodium ethoxide I get. This is fine with the primary alcohols. Now suppose there is secondary alcohol. Okay, let us assume secondary alcohol is there. Now primary alcohol, I have got this. Now secondary alcohol, what is going to happen? Just see, secondary alcohol, if you take, I think this is clear. Okay, let me check it is coming in the lens or not. Okay, so secondary alcohols, if I take, what is secondary alcohol? CH3OH means this alcohol is attached to 2 alkyl, means this carbon is attached to 2 alkyl groups and 1 OH, one functional group, that is secondary alcohol. Right, now this secondary alcohol, suppose if you are trying or if it is undergoing oxidation. Yes students, secondary alcohol is undergoing oxidation. So what happens when it undergoes oxidation? Secondary alcohols, they get converted to ketones, correct, isn't it? So what do they get converted into? Ketones, C double bond O CH3. Okay, this is ketone. Secondary alcohols to acetone or ketone. Done. Now suppose if I take tertiary alcohol, so this part is over. Now I'm going to take tertiary alcohol. So secondary alcohol will give us ketones on oxidation. Tertiary alcohols we will take. What are tertiary alcohols? Where the carbon is attached to 3 alkyl groups 1, 2, 3, 1, 2, 3 and OH. Suppose if you are allowing this to undergo oxidation, okay, will it undergo? Right. Remember, tertiary alcohols will not further undergo oxidation. Remember, no oxidation will happen. Done. Now, what can I do with this acetone? Remember, this acetone further, if you are introducing KCN, okay, you're introducing KCN to this and little sulfuric acid you're using, acidified. When you're using sulfuric acid, what happens? It's going to form a product called hydroxynitrile. What is the formula? Just see here, same thing I'm writing, CH3. Okay, this carbon is here because this is adding OH, this CH3 is here and your CN. So OH, CH3, CN. What is the name of this compound? Hydroxynitrile. So that is further ketones are converted into hydroxynitriles. This is fine. This is clear. Okay. Now further ketones, what can I do? Right? If I have to write further ketones, can I do something else? Let's see that also. So I think, okay, little bit I'll take from here. I'm taking ketones and making it, I'll draw it here. Okay. Now see. Further ketones I can perform or use 2,4-DNP, means I can do a this in using elimination addition reaction. What would I do? I can use something called addition and elimination. Both will happen in this. What am I going to use? I am going to use 2,4-DNP to this and warm it. Okay, 2,4-DNP and warm. When you use 2,4-DNP and warm, what happens? The product formed, this is your acetone, isn't it? Right? Just see here, CH3 is here only, carbon is here, so 2,4-dinitrophenylhydrazine, that phenylhydrazine adds to this carbon. So this is over. 2,4 at the second position, and at the fourth position you are getting this. What is this? This is nothing but an orange precipitate. Orange PPT is formed. This is what? One with KCN you get hydroxynitrile, one with 2,4-DNP you get an orange color precipitate, that is your 2,4-dinitrophenylhydrazone, where you add it to the ketonic group. This is also clear, students. Done. This is over. So primary alcohols, fine. I converted into haloalkenes, I converted into ketones, I converted that into the 2,4-DNP, that is hydrozones also. Now after this is over, our page is full. Let us take this out and come back. Now where did we stop? We have stopped at basically primary alcohols is over. Now let us again rewrite. Now what did we say? We have converted alkanes to alkyl halides, done. We have converted this into alkenes, done. Then we have converted this into your primary alcohols, that is also done. This primary alcohol is again converted to alkyl halide, done. This is fine. Now this alkyl halide is again converted into, as I said, it's converted into nitriles, rather ethyl cyanide. Okay, nitriles it is converted. It is also converted into amines, correct? Then this nitriles are further converted into carboxylic acid. Amines are further converted into, means the nitriles only. Nitriles further are converted into amines on reduction. Same thing, this is converted on reduction into amines. This is where I stopped, correct? Secondary alcohols I said, and tertiary alcohols. Now let us start. Further, primary alcohols, when I say, as I said, we are going to perform oxidation in the forward direction and reduction in the backward direction. This is your distilling part and this is your heating part. Now what happens? The primary alcohols on oxidation, or if I have to say, means you are basically, I have to take out hydrogen, correct? No. So here primary alcohols on oxidation, that is removal of hydrogen, addition of oxygen, that's fine. Here on distilling, what happens? They're going to get converted to aldehyde. So what aldehyde? It's going to get converted to CHO. Now let us see the reactions of these aldehydes. Okay, students? Yes. So here aldehydes, what happens? When we see aldehydes, when we take the aldehydes further on oxidation, I'm going to do the oxidation process to this, right? and heat it. Okay, O, oxidation and heat it. Further, again in the reverse direction, what am I going to do? I am going to do the reduction process and heat it. This is fine. What am I going to get? I am going to get an acid. Correct? We are going to get acid. So CH3, COOH. Now we are going to see the reactions of aldehydes. Little careful, students. Okay. Now I am going to take this aldehyde and show you the reactions. Now, when I take the aldehydic part, just see, let us put the aldehyde in the center. So the aldehyde which I have taken is CH3CHO. Right. Suppose if you are introducing to this aldehyde, okay, let us put a box for this. Done. Okay. Now to this aldehyde, if I am adding 2,4-DNP, I am adding, what am I going to add? I am going to add 2,4-DNP and warm it. What will happen? It is going to again form the same, just see, just as we did it in the ketones. Earlier ketones had CH3 here. Now aldehydes will have carbon, N, NH, NO2, 2,4, dinitrophenylhydrazone. This is fine. What is the color of the precipitate here? Again, the color of the precipitate is an orange PPT. This is also fine. Right? Now, important thing. Here, when we are introducing Tollens reagent and the Fellings reagent, this is what is important in aldehydes, correct? Yes. Now, when I take aldehydes, I am going to introduce Tollens reagent. What is Tollens reagent? It is nothing but ammonical silver nitrate. Okay. So, ammonical silver nitrate is the Tollens reagent which we are taking. The same thing I am introducing Felling solution also to this. Felling solution. What is Felling solution? We have Felling solution A and Felling solution B. Correct? Right? Right. So, here Felling solution is this and here is Tollens reagent. What happens in the Tollens reagent? Here Felling solution, I did one video on the Felling solution A. What is the reaction also? Here I am just writing the products. Please watch the video. Go to the aldehyde playlist and watch their Felling's test and Tollens test. Done. Here you're going to get or silver deposits out. Correct? No? Silver mirror test you get and CH3COO minus is out. Now, when I take or when I add Felling solution and just warm it, first Felling solution A you add, then Felling solution B and warm it. What do you get? You get a red precipitate of copper, red PPT of copper oxide. And see your CH3COO minus, sorry students, yes. So, CH3COO minus is out. This is fine? Okay. Now further aldehyde if I take and if I am performing a nucleophilic addition reaction and I am going to introduce HCN and NaCN at 10 to 20 degrees centigrade, 10 to 20 degrees centigrade, what do I get? I am going to get, see here, cyanohydrin. Remember students, you studied semicarbazide, cyanohydrins, formation of glyoxyl, hemiacetals, remember? Yes. So, this is your cyanohydrins. Further cyanohydrins, just see, if I am going to take the same cyanohydrin, we will see the different reactions. The same cyanohydrin, suppose, let me draw one reaction here, let me draw one more reaction here, let me draw one more reaction here, let me draw one more reaction here, right. So, the same cyanohydrin, is it visible students? Yes, okay. The same cyanohydrin, suppose if I take, just see here, if I am performing hydration and I am introducing dilute HCl and sulfuric acid, what product do I get? See here. Everything is the same, but here you are adding hydrogen, means hydration, water is added. Okay. Now what product you get? CH3, same, CH, COOH and OH. Suppose if you are performing reduction process, one hydrogen is added here, one more hydrogen is added here, CH3, CH, CH2, NH2, OH. This is fine, right? Clear students? Yes. Now, The same thing, like suppose if you take the cyanohydrin part, if you have to study the mechanism, how it is added, how nucleophilic addition is added, please watch that. There's no place here, so here I'll be mentioning the mechanism, how to add. And important thing, the arrow which I have mentioned here, this is for you to just go through addition, same procedure just like this, how you will be adding semi-carbazide, how you will be adding acetyls, how you will be adding methyl ketones. Please watch that. Methyl ketones, it will be very useful, the continuation part of this. This is fine. Okay, now aldehydes is over. Now what did we say? We said aldehydes are further converted into acids. How they are converted? I can convert aldehydes on oxidation and heating into carboxylic acids. That is your CH3COOH acids. Correct, students? Now acids in the reverse order. Suppose if you take in the reverse order, on reduction, get aldehydes, removal of oxygen basically. So now we will speak about your acids. What is going to happen to acids, how it is reacting. Students, now where did we stop? We have stopped at carboxylic acids. I have got through oxidation, carboxylic acid. Now let's see, suppose your carboxylic acid is there, right? That is your CH3COOH, your carboxylic acids. So this is your carboxylic acid. What can I do? Let us see the reactions of this, important reactions. Done. So basically, when you are introducing sodium metal to this, we very well know metal added, what does it form? It's going to release hydrogen and form a salt, COONA. Correct? No? This is fine. So there's a displacement of sodium and hydrogen gas comes out. The same thing if you want to convert back this sodium acetylide back to your acid, you can introduce HCl. If you introduce HCl, NaCl comes out and you get acid back. Done. Now, the same acetic acid, suppose if I'm introducing calcium carbonate. Okay, so I'm using calcium carbonate. Now I'm going to perform this experiment is RT. RT means room temperature. So RT stands for room temperature. So if I'm introducing or performing at room temperature, what happens is carbonate means which gas will come out? Carbon dioxide gas along with water. What happens? There's a cleavage of the bond and it forms calcium acetate, COO minus and calcium plus 2. Right, so 2 acetates and 2 calciums, plus 2 and minus 2, right? Right. So basically it means it's something like this taken twice. Now suppose the same acid if I take and perform esterification reaction, right? So for esterification, what happens? You're going to use an acid as well as alcohol, CH3CH2OH alcohol. Now what is required? You require sulfuric acid, dehydrating agent. So water is subtracted, water comes out and you will add both and it forms an ester, CH3COO CH2CH3. This is an ester, isn't it? Now further this ester if I have to take, just see here, if you are doing hydration and if you are introducing aqueous sodium hydroxide, the same thing, there is a cleavage of the bond here. Na adds here to this and OH adds here. What do I get? I am going to get CH3COONA aqueous and CH3CH2OH. That is your ethanol. Suppose the same ester if I am introducing, again the same hydration process only, and I am introducing dilute H plus ions, a dilute acid rather. The reverse reaction happens. Ester breaks up into acid and alcohol. This is fine. This is the reverse reaction of this one. Right, students? Done? So, next important. Suppose if I am taking the same acid. If I am introducing a base, your OH minus ion again at room temperature. RT means room temperature. So I'm introducing OH minus ion. What happens? Water molecule comes out. So if I take base means KOH, let us assume KOH. What do you get? CH3, COO minus, K plus, and water is out. So total how many reactions important? 1, 2, 3, 4, 5, 6, 7. This is your acid. Suppose if I am going to take, now I said no, acid is getting converted to acyl chlorides, the last one. So if I take acyl chlorides, CH3COCl, that is your acyl chlorides, To this acyl chlorides, you are introducing ammonia aqueous. What do you get? See here, CO, this part, the HCl comes out, breaking the bond, and you get CH3CONH2. What is this? This is amide. Correct, students? Now, to this amide, suppose if I am introducing dilute HCl aqueous. Just see here. At this point, oxygen is added because we have taken the aqueous part. So CH3, it gets converted to acid. Now, the same acyl chloride further again at RT, that is your room temperature, and the condition should be cold, and I am going to introduce methylamine. To this. Now see, same thing. You're going to write CH3CO, right? Now methylamine gets added to this CH3NH. So what is this? It is amide now. Yes, students. Basically, this got converted into amide. What is this amide? This is called N-substituted amide. This is fine. Perfect. So let us check everything, students. I have did all the conversions page wise. I think I'll put all the things for you all. Hope this is clear for you all. If anything, if I've missed out, I think I'll put it in the as a PDF also. I'll try to put it in the PDF. If anything I missed out, please let me know. All the things are here. One final thing I'll tell you. Simple. Alkanes are getting converted to, let us summarize once, alkanes are getting converted to alkenes, alkenes to primary alcohols to aldehydes, aldehydes to acids, acids to acyl chlorides. Correct, students? So basically, important thing, all these conversions or all these reactions have covered everything of your textbook, 99.9%. Maybe if I have missed out somewhere, please let me know. You can ask me, I'll tell you. So thank you for watching, students. Stay happy, stay connected. Hope you would have seen yesterday's video, that is your coronavirus video, how it went, how they could come back. So all of you stay safe. Good evening, students. Welcome to one more session of your World of Chemistry. That is, today we are going to do organic mapping. So basically, in the previous video I have done a mapping, that is your physical chemistry chapter, that is solid state. Now today we'll be doing haloalkanes, haloarenes chapter. So very nicely the whole chapter is done. Let us see that we are going to complete it in 40 minutes max, right? So here, whenever you're studying haloalkanes, haloarenes, as I have divided, we have classification done, and then I have physical properties, then I have preparations which are framed together, then I have chemical properties which are framed together, then I have racemization, that is your stereochemistry, and then last is the next would be the name reactions, and then last would be the polyhalogen compounds. Let's start off. Right, so when I have to speak about the classification of haloalkanes, haloarenes, the first important thing, let's see how are they classified. So basically haloalkanes and haloarenes are classified into two categories, means based on two categories, that is number of halogen atoms as well as based on hybridization. So if it is number of halogen atoms, haloarenes and haloalkanes, how are they classified? Let's see. So basically based on the number of halogen atoms, the haloarenes are classified into three. Basically, for example, the basic example, suppose I have an haloarene ring. This is monohaloarene. Then we have the second comes dihaloarene. The third comes, I am taking an haloarene ring, means a haloarene part, and I am going to add the halogens. Now see, haloarenes based on the number of halogen atoms. The first thing we have one halogen atom. Here we have two halogen atoms. Here 1, 2, 3 halogen atoms. So monohaloarene, dihaloarene, trihaloarene. So this is one classification. Suppose the same thing if I have to write it for haloalkene. Now see, haloalkene, no? Right, so alkene C2H5 I'm going to take and add one halogen to this. Done. Next, second type, I'm going to take CH2X, CH2X. I'm going to add two halogens to this. Now I'm going to divide this CH2X, CH2X and CH2X. Now how many halogens, students? 1. This is the first one, then 2, let us mark it as 1, this is as 2 and this is as 3. So one halogen, this is called monohaloalkene. Next, dihaloalkene, 1, 2, 3, trihaloalkane. This is the classification which is based on number of halogen atoms. Simple, isn't it? Now let us see the classification based on hybridization now. Hybridization, it can be sp2 hybridized CX bond or sp3 hybridized CX bond. Right. So suppose if it is sp2 hybridized CX bond, what are the two examples which you need to remember? Basically it is, the first one is vinylic halide. Vinylic halide. How is vinylic halide written? Just say you're going to write the double bond, immediately adjacent to this is the halogen. Next comes aryl halide. So aryl halide also, in this the CX bond is, what is the type of hybridization? Okay, that is sp2. Now I have an aryl ring, you have a halogen attached, these two are sp2 hybridized. When it comes to sp3 hybridized CX bond, what examples are we going to learn? Just see. So here in sp3 hybridized, first thing, three different classifications are there. First would be primary, secondary, tertiary, then allylic, then benzylic. Let us write. So here in the first classification, which is sp3 hybridized, suppose if I take one alkyl group, right? So one alkyl group, primary, second, this is two alkyl groups, secondary, three alkyl groups, this is tertiary. Done, isn't it? Right, these are all sp3 hybridized. Next comes in the B part, that is allylic halides. So here we have studied vinylic halide, here we are going to study allylic halide. Now what is the difference here? In allylic halide, adjacent to the double bond, there is CH2 group and then comes X. Remember that. Next, one more in the aryl form, which I can write, that is X. These two are allylic halides. Next comes benzylic. The last one is benzylic halides. Benzylic halides. So in benzylic halides, how is the structure written? I'll be writing it here, students. Right? So you have a benzene ring, alternate pi bonds, then CH2X. So see here, the halogen is not attached directly, but it is attached to a CH2 group and then to the benzene ring. So this is how the whole haloalkanes and haloarenes are classified. So once again, before going to the next page, let's see the classification. Haloalkanes, haloarenes are classified based on number of halogen atoms and based on hybridization. If it is number of halogen atoms, mono, di, tri haloarenes, mono, di, tri and haloalkanes. If it is based on hybridization, it is sp2 as well as sp3 hybridized. In sp2, we have two examples taken, that is vinyl halide or the vinylic halide. Also, yes, let us write vinylic halide, which is where the halogens directly attached to the double bond. Arylic halide, where The halogen is attached to the aryl ring. If it is sp3, we have primary, secondary, tertiary alkyl halides, then allylic halide where the halogen is attached to CH2 and CH2 is attached to double bond. So in benzylic halide also same thing, CH2, first is halogen attached to CH2 and then attached to benzene ring. Right students, this is done. Okay, now let us come and do the next important topic, that is your physical properties. Alright students, now welcome to the next session, that is your physical properties. Now basically physical properties, here on this side I have written or taken all the physical properties which you need to remember for your exam. That is for the haloalkanes, that in terms of solubility, density, stability, dipole moment, melting and boiling point. Done. Now when it comes to the haloarenes, the same category, that is solubility, density, stability, dipole moment, melting and boiling point. Now let us start off understanding this. So when I have to speak about the physical properties of haloalkanes, solubility. So basically haloalkanes and haloarenes both are immiscible in water. Why they are immiscible? Because they don't form hydrogen bonding. Correct? Yes. So let us write solubility, they are immiscible in water. Immiscible in water. Done. Then where are they miscible? Where are they dissolving? So here also same, but they are going to dissolve or miscible in organic solvents. Right students? So solubility, immiscibility in both the cases, and they are soluble in organic solvents like ethanol. Done. Next, density. So density, basically what do we remember? We remember density, we have studied the formula, density is equal to mass by volume. So density is directly related to mass. Yes or no? Yes. So here remember, because density is directly related to mass, if I have to write the order, Ri is greater in density than Rbr, which is greater in density than RCl, which is greater in density then RF, right? Yes. So what do you understand here? Remember, for the same alkyl group present, as a chlorine atom is differing, if the weight of the chlorine atom is more, higher, iodine has higher weight, higher mass compared to fluorine. So higher the mass of the alkyl group, higher the mass of the alkyl group, it is directly related, the density would be higher. So iodine molecular mass is higher, so the density is also higher in nature. If I take one more example, just see here. So here, see here, C3H7Cl greater than lesser than C3H7Br, which is lesser than C3H7I. That means, what am I trying to explain here? What are you saying? Here, carbon mass is same, C3, C3, C3. Carbon mass is same everywhere. But what is differing? Halogen mass is differing. So that's why here the density of C3H7Cl is 0.89 gram per ml. This is 0.33. This is 1.75. Okay. So here you should remember, if the alkyl group is same, if the halogen varies, so what is going to vary? If the mass is increasing, density also increases. So here mass, iodine mass is more, so the density also is higher. Here also see iodine mass is more, so the density also is higher. Right? Yes. Yeah. Now next important thing. Here you need to remember one more concept. Here in case of haloarenes also same thing, density is equal to mass by volume. So you can pick up the trend as I have given in terms of haloarenes also. Done. So now when I speak about stability, so stability order, see the stability order, RF is more stable than RCl, is more stable than RBr, this is more stable than Ri. Right? So when it comes to haloarenes, remember haloarenes are more stable compared to this. Why? Let us write are more stable. Why are they more stable? Because they can donate the lone pairs to the ring inside. Because haloarene is nothing but this one, isn't it? So what can they do? They can donate the lone pair of electrons present to the ring. So they are more stable because what is the reason, students? They can donate, what can they donate? Lone pair of electrons. They can donate lone pair of electrons to where? To the ring, So because of this, what will happen inside the ring? Resonance happens, isn't it? So let us write that, ring for resonance. Okay, my handwriting is a bit bigger, so the box is not sufficient. It's okay, for us content is important, right? Next, so this is the stability of both. When it comes to dipole moment, let us compare. So in haloalkanes dipole moment, remember the order is CH3Cl greater than CH3F greater than CH3Br greater than CH3I. Okay, now what is the reason why fluorine is chlorine is more greater than fluorine? Here remember CH3F, here the size of fluorine is very low, isn't it? Because of this, because of the size is very low, the dipole moment also of CH3F is low. That's the reason trend is like this. Okay, otherwise normally we write it in trend, you know. So because of the size, this one you need to remember the fluorine size is less, hence the trend followed is here. Now when it comes to haloarenes dipole moment, if I have to write, just see para dichloro, okay, para dichlorobenzene, okay, para dichlorobenzene, what is the dipole moment? 0.00 d by. The para dichlorobenzene doesn't have the dipole moment, it is 0, right? When it comes to ortho, it gets cancelled, isn't it? Okay, ortho dichlorobenzene, the dipole moment is 2.50. Ortho. So meta dichlorobenzene, the dipole is 1.72. So when I see the order, meta dichlorobenzene is greater than ortho, which is greater than para. So this is in case of your haloarenes. Done. So when it comes to melting and boiling point, let's see. So melting and boiling point, you need to remember one important concept, that is melting point and boiling point. If they are increasing, what you should remember? Remember, melting and boiling point increases with increase in size. Okay, increase in size. Done. Why they are increasing? Because higher van der Waals forces. So van der Waals forces, VF means van der Waals forces also are higher. Van der Waals forces are higher in nature or higher. That's the reason the melting and boiling point increases. Right, students? Now, so here also it's the same thing which is noted, but important things are examples we'll see. So you can correlate with this. So when it comes to the examples of the melting and boiling point of the haloalkanes on this side, just see the trend Ri is greater than Rbr, greater than Rcl, greater than Rf. Now what is the reason here? As I said, melting point increases. Same concept, as the melting point increases because the size increases. Now see here, as the size of the halogen increases, melting point increases. Why? Because the van der Waals forces are more in this case. Same thing I've applied here. In the second example, remember, suppose if I take this example, see here, 1 bromo, in terms of, this is in terms of your melting point. Now I'm writing in terms of boiling point. 1 bromobutane. Now I'm talking about isomeric alkyl halide. So 1 bromobutane is greater than 2 bromobutane, which is greater in boiling point than 2 methyl propane. So what am I trying to tell? All these three are isomeric alkyl halides. See here, I have only changed the position. So 1 bromobutane, in the first position bromine is there, 2 bromobutane, second position bromine is there. Now I have shifted the bromine to, the bromine is here, but the alkyl group has become 2 methyl propane. So what am I trying to say here? Isomeric alkyl halide. This is the trend in boiling point. When I have to write the boiling point trends of here, in this case aryl halide, just see students, same thing I'm writing here, that is ARI greater than ARBR greater than ARCl. That's over. Now in terms of isomeric halides, remember this. So in isomeric halides, what is that? Para chlorobenzene is greater than ortho or para dichlorobenzene. So I should write also ortho dichlorobenzene is greater than meta dichlorobenzene. So why is this? These are all isomeric dihalides. So what is happening here? What is the reason? Here what reason did we write? We have written isomeric halides. Here this is the order. Here in this case the reason is boiling point is decreasing as the branching increases and the surface area also decreases. Okay, in the other way let us understand. So in para-dichlorobenzene, what is happening here? It is packed, there's a close packing of the crystal lattice. Very closely it is packed. See here, it is symmetry, isn't it? If I write this benzene, one chlorine here, one chlorine here. So in the crystal lattice, it is closely packed. Because of this, the boiling point of para-dichlorobenzene is very, very high. So simple, isn't it, students? So once again, we'll summarize. So physical properties, haloalkanes, haloarenes, I have taken the category of solubility, density, stability, dipole moment, melting and boiling point. I have written the trends everywhere. This is a trend which you need to remember. Stability, this is a trend. Dipole moment, this is a trend, as well as melting and boiling point. So here also I have divided the trends which are very important for you all to remember. Little bit the paper is clumsy, but the content and the information is very, very important for you students. So let us come back and do the next page, that is preparations of your haloalkanes. This is the things which is listed, and preparations of haloarenes which are listed here. Now let us come back and start with the preparations of haloalkanes and haloarenes in one page. Now here in the haloalkanes preparation, we are going to obtain the haloalkanes from alcohols as well as free radical halogenation. So right, and when I have to prepare haloarenes, I am going to obtain haloarenes from benzene, phenol and BDC. So here we have alcohols and free radical halogenation of the alkanes. So here this is from alcohols, this is from alkanes, this is the thing, and here we have from benzene, phenol as well as BDC. Let's start. So here when you're going to take alcohols, just see students, the first thing whenever you see HCl and anhydrous ZnCl2, it's nothing but Lucas reagent, isn't it? Lucas reagent, the product is nothing but RCl plus water. Okay, what is the other name given to this? This is nothing but Groove's process, right? What is happening? The OH here is replaced by the nucleophile Cl. ROH was there, the Cl has replaced this and you get RCl and the leftover water. Next product, when it is NaBr plus sulfuric acid, again OH is replaced by Br, we get a product RBr plus water. Done. If it is PX3, right? So PX3 is nothing but PCl3, right? We are going to get a product that is RBr or Rx, because I have taken X there, Rx plus H3PO3. Here I have shown you in my earlier videos in haloalkanes, haloarenes chapter, how did I get this clearly. I have taken Cls. Please watch that video for this explanation. Now, if I take 5 chlorine atoms here, I'll be getting a product that is RCl plus POCl3 plus HCl. Now see here, 3 plus 1 4, 4 plus 1 5. So all the 5 chlorine atoms are balanced. Now when I take alcohol, when I treat it with pyridine and SOCl2, so thionyl chloride, isn't it? So the most important economical method for preparing haloalkanes, the products which I get is RCl, so thionyl chloride. Why is it economical here? Thionyl chloride will come out, or it comes out, it releases gases like sulfur dioxide as well as HCl gas also. So this is why it is called economical processes, and we get form of RCl here, right? So the name of this procedure is called Darzan's procedure, right? So this is called Groove's process, this is called Darzan's procedure. Yes students, here again I'm saying this is a mind mapping, this is a refreshing of all the reactions. For clear explanation, I have done all the videos, you can watch it, right? So when it comes to the free radical halogenation, let me move the page a little bit so that it's clear for you all, right? So free radical halogenation, what am I taking? I'm taking alkanes. So take an alkane, CH3, CH2, CH2, CH3. So whenever we say free radical halogenation, most important thing is you're going to take an halogen in the presence of UV light, isn't it? UV light and heat. This is what is important among everything, right? So every time you are going to replace one halogen, one hydrogen with the halogen, then this one. Let us see what products you get. So in the first case, free radical halogenation, CH3, CH2, CH2. I'm taking out one hydrogen from here and I'm going to replace with chlorine. One more product, CH3, CH2, CH. Now this hydrogen is replaced In that way, 1,1 you will be halogenating. So this is how you are going to prepare or do the free radical halogenation of alkanes. So I am going to get alkyl halide, 1 chlorobutane, 2 chlorobutane. So this is how it's prepared. So haloalkanes can be prepared from alcohols in this way, from alkenes in this way, right? Now let us prepare haloarenes. So haloarenes, if I have to prepare, I said we are going to prepare this from phenols. Here we have taken alcohols, here we are going to take phenols. What is the thing? So basically phenol, when I take benzene ring with OH, isn't it? Right. So how are we going to do? We are going to add PCl5 to this. So phosphorus pentachloride. What is it going to do? One hydrogen from here is replaced by chlorine. So I'm not preparing haloarene now. So chlorobenzene, haloarene, done. What is left out now? One H will come out as HCl and the leftover is POCl3. So let us count the chlorines. 3 plus 1 4, 4 plus 1 5. So simple, isn't it? So I have prepared haloarenes from phenols. Yes students, done. Now let us prepare from benzene. So here I am going to take benzene. How can I prepare? The simplest way is you are going to add chlorine to this. I need to add, and I am preparing haloarene, that is chlorobenzene. So take benzene, add chlorine. So what it is important in the presence of FeCl3 and dark. This is what is the condition important. The temperature is 310 to 320 Kelvin. So one hydrogen is replaced by chlorine and I am going to get chlorobenzene here and the HCl is out. Understood? Simple. I have prepared chlorobenzene from benzene. Done. What am I doing? I am doing halogenation. Halogenation is nothing but addition of the halogen to the benzene ring by replacement of one hydrogen. Done. Side chain halogenation. This is very simple reaction. Let's see. So first you are going to take toluene. Okay, toluene means benzene ring with CH3. You are going to halogenate with chlorine. Here you are going to use 383 Kelvin and you are going to use sunlight. Simple. So what is the side halogenation? 1 hydrogen from here is replaced by chlorine and the HCl comes out. So in the first product, what do I get? I get a compound called CH2Cl, right? So HCl is out. Again you are going to introduce with Cl2. Same conditions. Again one more hydrogen is replaced here. What do I get? I am going to get CHCl2. Means hydrogen is decreasing, halogen is increasing. Done students? Yes. Then further you are going to introduce with Cl2, means I am halogenating every time. Now hydrogen whatever is there is replaced by chlorine. We get CCl3. So see here I have got alkyl halide everywhere. So no, I'm sorry, not alkyl halide. As we have discussed in the first page, we have got, what is this compound? Benzyl halide, isn't it? Benzyl halide we have got in all the cases. So this is how we are going to prepare by side chain halogenation. Now next important preparation, I'm going to prepare haloarene, that is from BDC. BDC stands for benzene diazonium chloride. I have done a video also with this. Please watch, go to the playlist of haloalkanes, haloarenes, you will get this video. So basically there are 1, 2, 3, 4, 5, 6 very important you need to remember. So here important thing, why BDC is used, because it releases all the products while preparing haloarene, nitrogen comes out as nitrogen gas. So the leftover product is haloarene. Then let's see. Suppose if I introduce or take CuCl plus by HCl, what product do I get? So benzene ring, the product which I get is C6H5Cl. Okay, CuCl, HCl. So nitrogen gas every time, remember nitrogen gas is released. I will not write every time, but every time nitrogen gas is released. Okay, now you are introducing Br. So Br is replaced by HCl. You get C6H5Br plus nitrogen gas. Now these two reactions, when you are introducing, or these two reactions with BDC are called as Sand-Mears reactions. So remember, CuCl by HCl, CuBr by HBr is nothing but Sand-Mears reaction. Done. Next, you are taking BDC, you are introducing in the presence of copper and HCl, copper and HBr. What product you get? Same as Sand-Mears only, C6H5Cl one product. Here C6H5Br, but N2 is compulsory, N2 plus N2 everywhere. These two reactions where you are taking copper plus HCl is nothing but Gattermann's reaction. Gattermann's reaction, and these two reactions are called Sandmeyer's reaction. Sandmeyer's reactions. Okay, students? Yes. Okay. Right. Next I'm going to take one more important thing. I'm going to take BDC and introduce in the presence of HBF4 and at 273 Kelvin. So HBF4, when you're seeing simple, the fluorine will replace chlorine. Nitrogen comes out as gas. Remember, okay? Right. So what are we going to do? We are going to take this fluorine and the product we get, there is an intermediate product which I'm not writing here, C6H5F. So here this fluorine is replacing chlorine as well as N2 is out. So what is the name of this reaction? This reaction is called Bals-Schiemann reaction, okay, where you're preparing fluoroarenes. Next, potassium iodide. Simple. Here the nucleophile is I. I will go and replace Cl. So what do you get? C6H5I plus N2 as usual, and KCl is released here. Simple, students. So these are all the preparations, preparations of haloalkanes, haloarenes. Now we are going to see the chemical properties of your haloalkanes, haloarenes. Then I'll be doing the name reactions also. Hope you have noted all this. Little bit I'll move the paper above so that you can note it clearly, students. So all this I'm doing it for you only. I want everybody to come up in flying colors. Right. Let us come back and do the next thing, that is your chemical properties of haloalkanes, haloarenes. Students, welcome back. Next thing we are going to do now is chemical properties. Here I have divided the chemical properties for the haloalkanes on this side, for the haloarenes on this side. Done. So for the haloalkanes, the example which I have taken is C2H5Br, that is ethyl bromide. For here haloarenes I have taken ArCl, that is chlorobenzene, right? So or aryl chloride, right? So here we are going to see under different headings, that is nucleophilic substitution reactions, elimination reactions and reduction reactions. In case of haloarenes, nucleophilic substitution reactions and electrophilic substitution reactions. Done. So this is the important thing. These are the important. Then we are going to learn the Sn1 and Sn2 in terms of stereochemistry in the next thing. Now let's see. So when I have to speak about the chemical properties, I think the page is clear, students. Let me adjust my lens a little bit if it is not clear. Okay. Right, student. Now, when I take the haloalkanes, so suppose if you see in the exam potassium hydroxide aqueous, simple, the bromine is replaced by OH. Simple, isn't it? So with the bromine is replaced by OH nucleophile, the product which you get is C2H5OH plus nothing but KBr. Simple. So aqueous, when you see, that is what you need to remember. Right. Next thing. Suppose if you see ammonia, right? So this type of reaction is called Hoffman's ammonolysis. What is the reaction? Hoffman's ammonolysis. You will be getting different products. Let's see. Simple. You take C2H5. So you write C2H5. In the case of ammonia, NH2. Okay. Done. One more product which you get. You will be getting C2, little space constraint, C2H5 taken twice, NH. Okay, I'll write the product here, students, for you. Right, next one, C2H5 taken thrice, N. Next, C2H5 taken 4 times, N plus Br minus. So a different, a combination of different products you'll be getting where the number of alkyl groups are increasing. So this reaction is called what? Hoffman's ammonolysis. Right. Next thing. Suppose if you are having, or if you see in the exam, potassium cyanide is there, silver cyanide is there. Remember, potassium cyanide, you will be getting a compound that is C2H5Cn plus KBr. If you take silver cyanide, you will be getting a product C2H5NC plus AgCN. Sorry, AgBr. So remember that important thing. Let me mark with one more pen. So whenever you see AgCN, you get an isocyanide. Whenever you see KCN, you get a cyanide compound. Okay, students? Done? Right. Next important, ma'am, what is the reason? I've also done a video on this. Please watch that. You could, if you go to Halo Alkenes, Salivarines, there you can see the video which is kept with the reason. Suppose if you have a KNO2 and AgNO2, remember both. If you have KNO2, you'll be getting a product that is C2H5ONO plus KBr. Remember, ambidentate nucleophile. Here, if it is AgNO2, you will be getting C2H5NO2 plus AgBr. Okay, students. Now, what is this type of reaction? This is called Williamson synthesis. What is this? Williamson synthesis. Now, when Williamson synthesis is, I'm really sorry. This is the reaction which I'm going to write is Williamson synthesis. I'm really sorry, students. So, if ethyl bromide reacts with RONA, okay, RONA, look here, Na from here, Br from here comes out as NaBr, okay, and what is attached? C2H5O and R. So this is Williamson synthesis. Williamson synthesis is this formation of ethers. Done. Next, if I take sodium acetylide in the presence of alkyl halide, simple students, see here, you're going to take C2H5, isn't it? Right. So you take C2H5 first. Then you're going to write the C. Then triple bond. This CH is there, this CH is already there. Then what is coming out? Na comes out with Br as NaBr. Done, students? Hope this is clear. Yes, done. Next comes, when you take RCOAg and heat it. Simple product. See here, AgBr will come out first. AgBr. Take out AgBr from here, and what do you get? The leftover is C2H5O. COR. So nothing but I'm writing the product here, C2H5O C double bond O R prime. So this is a thing. So these are the reactions, nucleophilic substitution reactions of haloalkenes. Now when it comes to the elimination reactions, right, students? So elimination reactions, let's see where we are going to follow the Saytzeff rule clearly, where we understand that what actually is a major product and what is a minor product. Right, students. Now let's see. So in the elimination reaction, what is important you need to remember, that is alcoholic KOH. Here you have seen the first reaction. Here we have taken aqueous KOH. When aqueous KOH is taken, directly you get a nucleophilic substitution. When this nucleophile Br is replaced by OH minus, and you get this. You get a product. Now here when it is alcoholic KOH, it's going to elimination will dominate over substitution. So we are going to get two different products, and this rule we are going to follow Saytzeff rule to do this. Saytzeff rule. Let's see. So here in this reaction, we have taken, what did we take? We have taken CH3, CH2, CHBr and CH3. So in the presence of alcohol, what did we say? We said elimination will dominate substitution. We are going to get two products. That is, first important thing, CH3 is here. CH. Now see here, this H and Br comes out, and you get this bond is shifted here. You get a double bond CH CH3. So what is this compound? This is but nothing but but-2-ene. 1, 2. So but-2-ene. Right. So next one more product. You get one more product, CH3, CH2, CH double bond CH2. So this is nothing but but-1-ene. So this is but-2-ene, this is but-1-ene. Remember, in elimination reaction, and that too if it is alcoholic KOH, in the presence of alcoholic KOH, not aqueous, in elimination alcoholic KOH, it follows Saytzeff rule, where the highly substituted alkene, that is butene. This is the major product. Let me take one more pen and write. So this is the major product which we are going to have. So butene is a major product. This is the minor product which we are going to get. So remember, students, so here in elimination reaction, butene is a major product compared to but1ene. Done. So next, let us do the reduction process. Right now, what is reduction? It's nothing but addition of hydrogen in the presence of a metal catalyst. So here we are going to add hydrogen in the presence of nickel. Then we are going to add Hi. Okay, Hi, an electronegative atom also. That is what we have studied, isn't it? Okay, so addition of hydrogen I am adding here in the presence of nickel. Addition of hydrogen I am adding in the presence of red phosphorus. Nothing. Here H2 is there, isn't it? You take out one H and one Br as HBr. Here also I is there, this I and this I. Both these I's will come out as, I hope this is clear, both these I's will come out as I2. Okay, students? Right. This H and this Br has come out as HBr. Right, one I and one I comes out. Now the leftover H add to this and it becomes C2H6. Simple addition of hydrogen. Now come here, C2H5 and H becomes C2H6. Done. So these are the reactions. So all these reactions are there for the chemical properties of haloalkenes. Done, students? Right. Now let us come back and do the chemical properties of your haloarenes. This is clear, students? Yes. So here the first chemical property, that is nothing but nucleophilic substitution reaction. Whenever you are taking ArCl, there are different temperatures here. 623 Kelvin, 443 Kelvin, just warming. Remember, it's 623 Kelvin when you take ArCl and add sodium hydroxide. What is the nucleophile here? It is nothing but OH minus. Correct, students? OH minus is the nucleophile. Yes. So OH minus is replaced by Cl and we get a product that is nothing but phenol. Simple. That's over at 623 Kelvin. Suppose if you are taking further, means if you are further taking NaOH and you are introducing that, now what is going to happen? Let's see. So here in exam, most of the students get confused. What they do, temperature they'll forget. They will go and write the product simply and come out. But important thing is they may give you from both the sides. Temperatures they may exchange. They may exchange the nucleophile there. But while studying the reaction, here see here, all three are sodium hydroxides only. But what is varying there? Here 623 Kelvin is there. Here what is happening? 443 Kelvin is there, isn't it? Here what is happening? You have just warming. So you need to remember the temperatures and go, students. Simply don't go and write. Right? Yeah. Now just see here at 443 Kelvin. Suppose now one example I have taken as chlorobenzene. Here, suppose at 443 Kelvin in the exam, they give you a compound that is chlorobenzene with an electron withdrawing group NO2. So, I am going to use this at this place. I am going to use this also at this place. So, at 443 Kelvin, what is happening? This NO2 is an electron withdrawing group. It will start increasing the reactivity or increasing the reactivity of this compound. So immediately the Cl is replaced by OH. So what product do I get? I am going to get, and here it was Cl. Now this becomes OH and NO2. Because this is increasing the electron reactivity. Now when you just warm it, just see it is going to add, just warm, only warming. The nitro group will add to all the ortho, para and ortho positions. Okay, all the three positions it occupies. But here for getting this, you need to take the three compound, that is chlorobenzene with NO2 here, NO2 here, NO2 here. Then only you can get, isn't it? So I'm going to take NO2 on 2,4,6 trinitro aryl halide. So I'm going to take, or 2,4,6 trinitro-chlorobenzene. I'm going to take this, and when I warm it, so because NO2 is highly reactive, the Cl is replaced by OH. Simple, isn't it? Done. This is over. Now let us take the next reaction, that is your electrophilic substitution reaction. So it undergoes halogenation, nitration and sulfonation. So Friedel-Crafts alkylation acylation I have done in the name reactions. So halogenation, the electrophile is Cl2. In nitration, the electrophile is NO2. In sulfonation, the electrophile is SO3H. Correct, students? So you will be getting two products. One would be the ortho product. One would be the para product. So both you products you get, ortho is here, para is here. Next, here which is major? Always remember. First let us name this. What is this? This is called 1,2-dichlorobenzene. This is called 1,4-dichlorobenzene. So which is major in both? Always remember. Let me take a pen and for you. So always remember the para product is a major product. Okay, right. Next comes nitration. What is electrophile here? You're going to get an electrophile. Now what are we going to take? We are going to take chloro. Okay, chloro. And one is orthonitro. Okay, one is 1-chloro-2-nitrobenzene. Next product is 1-chloro-4-nitrobenzene. So what is a major product? As I said, always nitro is a major product. Oh, sorry, the para is a major product. Remember that. Next thing, before sulfonation, the electrophile is NO2. So you're going to take chlorobenzene, and the sulfonation, the electrophile is SO3H. So you going to get one product as ortho. You're going to get one more product. I'll move my page a little bit above. Okay, one more product I get as para. So let us name this compound. This is nothing but, what is this compound? Okay, 2-chloro-benzene sulfonic acid. Okay, yes, this is called now 4-chloro-benzene sulfonic acid. What is major? Para is always major, student. Remember, this is major. So these are the nucleophilic substitution reactions and electrophilic substitution reactions. So hope this is clear. We have seen the preparations, we have seen the chemical properties, right? I'll move the page a little bit so that you can note it, students, little bit above also, so that you can have a clear understanding. Right, now in the next video, what am I going to see? Okay, let me keep it for some time so that you can pause your video and see, and then move this towards little bit above. You pause your video again, note it. Right. Now next video, next would be, I'll be teaching the racemization process, that is the stereochemistry part of haloalkene salivarine in terms of Sn1 and Sn2 reaction. Right. Welcome, students, to one more session, that is your stereochemistry. So in the previous one, what did we watch? We've seen the chemical properties, isn't it? Right. Now when we see the stereochemistry part of haloalkene salivarines, basically it's going to, when you see the mechanisms rather, it's going to show Sn1 and Sn2 mechanisms. I did a detailed video on Sn1 and Sn2 mechanisms. Please watch that video. So here we are going to, I have clubbed both the things. That is Sn1 mechanism, which follows racemization. That is, here you're going to get a mixture of both the enantiomeric forms, right? And when it comes to the Sn2 mechanism, it is nothing but the stereochemical inversion. Let's see both, right? So when I have to speak about racemization, simple. Suppose you're going to take, first important thing you remember, Sn1 follows the order tertiary greater than secondary greater than primary, right? Now suppose if you're going to take carbon with one alkyl group, okay, let me write little bit, I'm sorry, tertiary, one alkyl group here, one more alkyl group, right? So R1 will be here, R2 will be here, R3 will be here. Now here in this case, when I have to draw or pick that symmetry, here I have a nucleophile which is attacking from back. So this is the planar carbocation which is going to affect. The nucleophile will attack from here, or the nucleophile can attack from here. So when it attacks, you'll be getting two different products, a mixture of both, that is R1, I mean the racemic mixture of both, here R2, R1, R3. As I am again saying, I did this video, students, you can watch it. very clearly I did. Because now it is only mind mapping, I'm just writing the mechanisms. So these two are enantiomeric racemization products. Okay, students, where there is no inversion configuration, we have just written both the products. So this is called, what is this called? Enantiomeric racemization. Let me write this. This is called enantiomeric racemization, where we have taken tertiary greater than secondary greater than primary. Right, now when I have to take the Sn1 mechanism, here what you should remember, let me take my scale and draw one line so that it's not confusing for you all. Right, so in Sn1 mechanism, what is Sn2 mechanism, what is the order of preference? Here primary greater than secondary greater than tertiary. Done. Here in this case you're going to take a primary carbocation. So primary means only one alkyl group, right? So primary greater than secondary then tertiary. So for your example, to show the variation in group, here I'm going to take a secondary carbocation, R group, carbon. Now two alkyl groups, R1. Okay, this is R1 and one is H, right? One is X. This is the alkyl halide. So secondary, because two alkyl groups are there. Now when I take a nucleophile, electron rich species, it's going to attack this carbocation from here. What are you going to get? You're going to get a transition state in this way. How does the compound look? Carbon in the center, you have nucleophile here, you have one more which is in transition state, which is temporary. Right, students, which is temporary in nature, and here you have R prime, this is H, and down you have R2, right? Now see, all groups are, this is a transition intermittent state. Further, there is more removal of this X minus. What do you get? Immediately there is an inversion, just like an umbrella, it inverts in the configuration. Earlier H, I'll put the paper a little bit above, here H, R, all both the alkyl groups and the halogens on this side. Now it will invert in the configuration in this way, just like an umbrella. Nucleophile comes on this side, carbon with all the groups attached to this R1, R2. So here also you can write no problem, or you can leave this R and make this as R1. It's okay, just two different alkyl groups. So what are you saying here? Nucleophile is attacked from backside, from here, and here the nucleophile is formed. This whole whatever was there, all the three groups have inverted on this side. So that's why we have written a stereochemical inversion. So when I take the order of the nucleophiles, now the nucleophile order in which it prefers, and see the order, Cn minus is greater than I minus, it is greater than your OH minus, which is greater than CH3COO minus. All these are nucleophiles. Water greater than F minus. So this is the order of the selection of nucleophiles. So Cn minus is highly preferred as a nucleophile. Yes, so this concept I have explained, Sn1 mechanism as well as Sn2 mechanism. I have taken the order also here for Sn1, tertiary greater than secondary greater than primary. For Sn2, primary greater than secondary greater than tertiary. So I have written the enantiomeric mixture here. That is racemization. Both the enantiomers are there for at the part of this. That's why we call it as racemization. And Sn2, there is an inversion in configuration. Right, now let us come back and do the next topic, that is your name reactions, all the name reactions of the chapter, which is here. Students, now let's come back and do the name reactions. Last but one topic. We have seen what did we see? Let's see. We have seen the classification, then we have seen the preparations, then we have seen the chemical properties, then we have seen the stereochemistry part of it. Now we are going to see all the name reactions of the chapter. I think different channels will be giving different name reactions. I have clubbed all the name reactions which you need to remember. If you remember this, all will be covered in this chapter. Right. So when I have to see the idea of doing this, here on the right hand side we have I have written the haloalkanes. on the left hand side I have written Haloarenes. Done. So when I have to speak about Woods reaction, right? So in the Woods reaction, the first one, what is remember here, see here, Woods reaction, this is Fittig reaction. This is Woods Fittig reaction is common to both. Right? Now, here in Woods reaction, what is important? You're going to take an alkyl halide and you're going to add sodium metal and you're going to take one more alkyl halide on this side. Right? What is important in the presence of dry ether? I did a video explaining what is the role of dry ether. Right? So NaX, 2 NaX will come out and you're going to form a hydrocarbon with 2 NaX. So the preparation of an hydrocarbon in the presence of sodium and dry ether is nothing but Woods reaction. So when it comes to Woods Fittig reaction, here you're going to take C6H5Cl. Woods Fittig means one aryl halide as well as sodium as usual, and one alkyl halide would be there. Dry ether is a similar thing in both the cases. Here 2 NaCl will come out. 2 NaCl will come out. What is the product? C6H5 and CH3. So C6H5 and CH3. So this is Woods Fittig reaction. So in Woods reaction, 2 alkyl halides. In Woods Fittig reaction, 1 aryl halide and 1 alkyl halide. Right? So this is the thing. Okay, next thing, let us see reaction with metals. So in reaction with metals, what am I going to take? I am going to take C2H5Br, one alkyl halide. I am going to take one metal as mentioned here, magnesium, in the presence of dry ether. Again, I am telling you students, I have done a video. What is the role of dry ether? I have explained. Please watch that. So MgBr comes out. Adding with C2H5 together, you get a product C2H5 MgBr, ethyl magnesium bromide, nothing but the Grignard's reagent. Right? We are going to prepare Grignard's reagent, adding magnesium in the presence of dry ether. Now, next name reaction is isomerization reaction. Isomer means having the same structural molecular formula but difference in arrangement of the function group. Whichever function, you will place it at one position in this case, and the next case you will write isomer. It's nothing, simple. I'll see. CH3, CH2, CH2, Cl is here. Okay, CH2 and Cl. Now what am I going to do? I am going to heat it at 573 Kelvin and I am going to use anhydrous AlCl3. Right. Now from here, now this is in how many? What is this compound? 1-chlorobutane. Now on isomerization, this chlorine is going to shift to this carbon. First it was on the first carbon. Now CH3, CH2, CH, Cl, CH3. Shifted, isn't it? So these two are isomers. Right, students? Done. Next important thing, Finkelstein reaction and Schwarz reaction. Okay, in Finkelstein reaction, what is the thing? Let us take, in Finkelstein, as the name suggests, we are going to prepare iodoalkenes. Preparing iodoalkenes, or iodoalkenes is important. And in Schwarz reaction, we are going to prepare fluoroalkenes. Okay, students? Right. Now in Finkelstein, what am I going to take? I am going to take alkyl halide. I am going to add NaI. Here X can be chlorine, bromine, right? So here if I take NaI, now what is happening? The X is replaced by I and you get Ri. So are we not preparing iodoalkenes here? Iodoalkenes, right? And along with this, what is coming out? NaX. Done. In Schwarz reaction, what are we preparing? Fluoroalkenes. So what are we going to take? We are going to take CH3Br. This is going to take, and as I said, fluoroalkene. To prepare that, I am going to take AgF. Okay, silver fluoride I am going to take. When I take AgF, what is happening? The bromine is replaced by fluorine and I get CH3CF plus AgBr. This AgBr, whatever is there, it comes out as AgBr. Okay, students, AgBr. So this is Schwarz reaction. This is one of the name reaction of haloalkenes. Now Hunts-Decker reaction, simple. Already we have done this. Let's see. Hunts-Decker means nothing. You are preparing bromo. Alkyl means alkyl halide. You are going to prepare methyl bromide. But important thing here is in Hunts-Decker, you are going to take silver salts. See here, silver acetate plus bromine. This is what is important. And important thing is you're going to perform this reaction in the presence of CCl4. What product you get? You get CH3Br and plus AgBr plus your product which is formed. And important thing is carbon dioxide here. This is what is important. So Hunt-Stecker reaction, you're preparing bromomethane, and along with that silver bromide and carbon dioxide gas which is there, it comes out. So this is Hunt-Stecker reaction, right students? Yes. Now let us do the Fittig reaction. So Fittig reaction is nothing. You're going to take two benzene rings, one benzene ring here, along with this two sodiums you're going to take, and you are two rings and two sodium atoms you're going to take. Here you're going to perform this in the presence of ether. Then you get two benzene rings attached in this way, like this is called as biphenyl. Okay, you can draw it like this also, in this way. Okay, this is biphenyl. Done? Yes students. Now, so this is Fittig. Fittig reaction means two aryl rings will be there. Wurtz-Fittig means one aryl and one alkyl will be there. Done. So here in Wurtz-Fittig, again the same reaction, whatever is here, it is similar. Aryl halide and alkyl halide you add and you get a toluene, right? Next, in Ullmann reaction we'll see. In Ullmann reaction is nothing. You're going to take iodoarine, okay, iodobenzene, and you're going to add copper powder to this. When you add copper powder to this, right, you get, suppose this copper I is a CuI comes out, and two rings of this, and you get biphenyl. This is nothing but Ullmann reaction. Yes students? Yes, done. Next, Friedel-Crafts alkylation and acylation, right? This is an electrophilic substitution reaction. Now, in Friedel-Crafts alkylation, you'll be taking chlorobenzene. Now, in Friedel-Crafts acylation also, you'll be taking chlorobenzene only. Okay, but what is the difference? In Friedel-Crafts alkylation, you'll be adding as an electrophile CH3Cl in the presence of anhydrous AlCl3. Anhydrous AlCl3. Here in this case you will be adding acyl group CH3COCl in the presence of anhydrous AlCl3. Remember that. In both the cases you will be getting both the products, right? What is this? In this case, first case, I will be writing this products here. You will be getting two varieties of product. One product is methyl group, here is electrophile, and one more product is at the ortho position, one more product is at the para position. Okay, what is the name of this compound here? The name of this compound is 1-chloro-2-methyl benzene. What is the name of this compound? 1-chloro-4-methyl benzene. So what is the major product? Always I said the para group is a major product. Now, when I take the second reaction acyl, here you need to break it here. What is electrophile? CH3CO is electrophile. You get two products. One thing is chloro with the electrophile is COCH3, the ortho position, and one more is the electrophile at the para position, COCH3. Okay, so let us read this. This is, what is the name of this compound? Okay, let us see. Yeah, 2-chloroacetophenone. This is 4-chloroacetophenone. 2-chloroacetophenone and 4-chloroacetophenone. Clear students? Yes. So the acyl group is attached to the benzene ring. That's why it is called Friedel-Crafts acylation. Last reaction, that is Sand-Meyer's reaction. I did it already. In Sand-Meyer's, you're going to take first BDC, N2Cl. What are you going to introduce? You're going to introduce CuCl by HCl or CuBr by HCl. What happens? You get two different products. So in BDC, what is important thing? Nitrogen gas comes out. That is important. So both the cases, nitrogen gas comes out. That's why BDC, the product formed, we get the pure form of it. So Cl goes and means what happens? N2 is coming out. When you introduce CuCl, you get a aryl halide, that is Cl. If you take Br, you get an bromohalide, aryl. This is chlorobenzene, bromobenzene. This is your Sn reaction, right students? So please note it. All the reactions, name reactions are here. Very important for you all. You need to understand the name reaction and remember the products. So I'll just put it clearly for you all. So this is the first name reaction which I have written, and the last name reaction. I think it's clear. You can note it in your paper. Now the last topic of the chapter, that is polyhalogen compounds. So polyhalogen compounds, they'll be asking you the different applications, the uses of it. So polyhalogen compounds: chloroform, carbon tetrachloride, iodoform, freons, DDT and dichloromethane. I have noted the important uses of this. So chloroform is used as a solvent for fats and alkaloids and production of freons. Carbon tetrachloride used for the manufacturing of refrigerants and propellants and cleaning fluid, and iodoform is used as an antiseptic. So again, freons, these are the uses. DDT, which is used as an insecticide, and dichloromethane is used as a paint remover, propellant in aerosols and metal cleaning. So basically I have done all the topic, students, one after the other. See, this is your polyhalogen compound uses. This is your name reactions. Okay, I'll take out all my papers and tell you again. And this is your chemical properties which I have made. Then comes your racemization which I made. Then comes your preparations which I did. Then comes your physical properties which I did, and then comes your classification which I did. So thank you for watching, students. This is the complete video which I have planned for you all. Hope you would have all liked it. Thank you for watching. I'll meet you again with my next video, that is your mind mapping of your inorganic chemistry. Stay happy, stay blessed. Please share it among your friends. Your support is always required for World of Chemistry. Good evening, students. Welcome back to one more session of your World of Chemistry, that is your mind maps. So recently, I think 2 days before, I have kept in the community tab, I said, students, please vote. What do you want? I said I've given an option of hydrogen, redox reactions, mind map and grade 10 syllabus. So maximum votes were, I think you have all voted for mind mapping. So I've decided to go with all the mind maps of grade 12. Right. So in this grade 12, all the 16 chapters will be covered from my side. But one thing you need to promise me, students, unless until you watch the video, unless until it is shared with your friends, I can't go further. I expect more and more number of students to watch this. Because if you're, let it be your JEE exam, let it be your NEET exam, let it be any sort of competitive exam, this particular mind mapping from NCERT, completely 100% from the NCERT, every word is taken up in this. So I have prepared a template. So let's start off with the first chapter, that is solid state. I'll be uploading the video for all the 16 chapters. My request is you need to watch it on regular basis and make this a huge success, students. So let's start off. So whenever I take or speak about solid state, first of all, solid state, let us see what we have. We have classification, isn't it? So in your first chapter in NCERT, basically solid state, one side we have classification, and the other side we have a topic called crystal lattice. So when we speak about the classification of solid state, how many classes it is divided into? It is divided into amorphous solids, right? And the second category is crystalline solids, isn't it? Done. So what are amorphous solids basically? Amorphous solids are those in which the particles have irregular shape, correct? So I will not write the full definition, I will write irregular shape. So particles have here irregular shape. Done. That is the first thing about this. When I come to crystalline solids, most important thing, as I have said, the quite opposite here. If it is irregular shape, here in crystalline solids, it is the particles are arranged in a regular shape. That is an important thing. Done, the students. Now crystalline solids, again they are of large number, and these are again divided into 1, 2, 3, 4. 4 varieties. So the first variety, if I have to take, let us start from here. Here the first variety which is divided is nothing but molecular solids. So if I have to write, the first variety of classification of crystalline solids is molecular solids. So molecular solids are again further divided into 1, 2 and 3 variety. The first variety of the molecular solids is nothing but non-polar solids. Okay. The second category of the molecular solids are polar solids. Done. The third category of molecular solids are hydrogen bonded solids. Done. Further, after molecular solids, there is one more classification of crystalline solids, that is nothing but ionic solids. Ionic solids. Let us come back and write the definition later. The next category of crystalline solids which it is divided into is, after molecular, after ionic, next comes covalent solids. Covalent solids. After covalent solids, there is one more category of crystalline solids, that is nothing but metallic solids. Easy, students? Done. So classification, it's divided into amorphous solids which have irregular shape, crystalline solids which have regular shape, as well as it is again further divided into molecular, ionic, covalent and metallic. Further, molecular solids are again divided into non-polar, polar and hydrogen bonded. So when I have to speak about the molecular solids, right, let us see the definition. I'll just tell you the definition, you can note it because the place is very less. I'll write the examples. So whenever we speak about molecular solids, and that too which is a classification of the crystalline solids, you need to remember that here in molecular solids, what are the constituent particles? Nothing but molecules. So you can write in your books, molecular solids are those compounds in which molecules held by intermolecular forces. Means all the molecules are held tight together by intermolecular forces. If I have to take an example, methane is one example, glucose is one more example. Right? So molecular solids, what are they for? Particles arranged, that is molecules which hold the crystal lattice together by intermolecular forces. Now when it comes to non-polar solids, here what are the constituent particles? In non-polar, it can be atoms or molecules, right? But what are the forces which are acting? So atoms and molecules are held by weak dispersion forces or London forces, remember. So I'm writing the forces here. In non-polar solids, London forces or dispersion forces will be acting. So what is the best example of this? Argon and helium. Done. When it comes to polar solids, here molecules, here we said atoms and molecules, it can be atoms or molecules which can be held by dispersion forces. In case of polar, molecules will be held together by which forces? The forces which are acting are dipole forces. So dipole forces will be acting in this. If I have to take an example, sulfur dioxide, HCl are one more example. Suppose if I am talking about hydrogen bonded, here molecules again, here molecules are held together by which bonding? Hydrogen bonding, as the name suggests, they are held together by hydrogen bonding. Right, students? Done. So here the example is water, nothing but ice. Simple, isn't it? So let us come back. In crystalline solids, solids are classified into amorphous solids and crystalline solids. Crystalline solids are again divided into molecular solids, ionic, covalent and metallic. Molecular solids are again further divided into non-polar, polar and hydrogen bonded. Done. Now let us come back to ionic solids. In ionic solids, what is that speciality? Here basically ionic solids, as the name suggests, ions only are the constituent particles. So ions are held by what? They are held by strong Coulombic, spelling little bit C-O-U-L-U-M-B-I-C, strong Coulombic forces. So if I have to take the example of this common thing, NaCl is one example, MgO is one more example. Yes, students? Done. So here the ions are held by strong Coulombic forces. Now when it comes to covalent bonding, in covalent bonding we basically talk about non-metals. Here non-metals, what are they held with? They held with covalent bond. So non-metals are held by covalent bond. So give me some examples of covalent bond compounds. Covalent bond. So covalent bond, when I have to take, the examples are, best examples are silicon carbide. Yes students, silicon carbide, carbon is one more example. So when I take the last classification of metallic solids, as the name suggests, here in metallic solids the metal atoms are held by which bond? Metallic bond. So I am writing metallic atoms by which bond? Metallic bond. MB I am writing, metallic bond. So examples are, you can take any metal, iron, copper, like that, any metals you can write. So this is how this is the most important thing which you need to remember. You need to remember the name of the solid, as well as you need to remember what is the type of force acting in that, right students? Right students, now after this classification, let's come back to the basic unit of the solid state, that is we speak in terms of crystal lattice, isn't it? So the packing of the solids is in what? Basically they are packed in the form of a crystal lattice. Now crystal lattice, what is the smallest unit? If I have to write in crystal lattice, I am using a black pen now. I think it is clearly visible. So in crystal lattice, the smallest unit is nothing but unit cell. Yes, so here in unit cell we are going to calculate the density also. We are also going to see the types of unit cells, correct? Yes. So when to calculate the density of the unit cell, the formula which we use, so density in this way is equal to Z capital M by A cube Na, right? So this is a formula which we are going to use directly. You may be given one quantity, this one may be missing, you need to calculate remaining. This is given, you need to prove that density is so much, like that different variations will be given to each, right? So Na is the Avogadro number. Done. So here again in unit cell they are classified into primitive unit cells and centered. So this first category here would be primitive, P-R-I-M-I-T-I-V-E, primitive unit cell is one category. The second category is nothing but centered unit cells, right? So primitive unit cells are those where, what is this here? Particles are only at the corner positions. In primitive, all the particles are at the corner. But here in centered, we have again three varieties that we'll be writing very soon. First we'll finish this. So in unit cell in primitive, what should you remember? Particles are only on corner position, this is the concept, right? So here when I have to speak, we have different types, that is we call the Bravais lattices. There are 1, 2, 3, 4, 5, 6, 7 varieties of Bravais lattices. So the first variety which you should remember is cubic. Correct. So in cubic you need to remember the bond angles, that is the edge lengths, that is alpha, beta and gamma. Here what is the important speciality of cubic? Here basically alpha is equal to beta is equal to gamma is equal to 90 degrees. This is done, isn't it? Now if I have to see the example of cubic lattice, sodium chloride is example, polonium is example, copper is example of cubic crystal lattice. Done? Yes. Next thing, next is a tetragonal structure. So when I go with the tetragonal Bravais lattices, what is the thing? This is also primitive in nature, as you have written here. Alpha is equal to beta is equal to gamma is equal to 90 degrees. Right here examples would be tin, SnO2, TiO2. The next category is the orthorhombic variety of Bravais lattices. In this, A is not equal to B is not equal to C. In other terms, alpha, beta is gamma is equal to 90 degrees, but the edge length A is not equal to B is equal to not equal to C. Here in this case, everywhere it's 90, but here what is the thing? A is equal to B is not equal to C in case of tetragonal. In case of cubic, when we write A is equal to B is equal to C. Done, students. Now orthorhombic, when I have to give example, gallium is one example, barium sulfate is one example, potassium nitrate is one example. The next category here is, now here again ma'am, what is alpha, beta, gamma? Here alpha, beta, gamma is the same as above, exactly the same. Alpha is equal to beta is equal to gamma, 90 degrees. Now when we come to the next variety, that is a hexagonal type of Bravais lattices. So in hexagonal, again here A is equal to B, which is not equal to C. So again here angles, when bond angles, when we write, alpha is equal to beta, which is 90 degree, and gamma is 120 degree. Yes students, done. Next comes rhombohedral. So in rhombohedral, the other name rhombohedral is the triclinic, isn't it? So in rhombohedral, when we take the examples are tin, mercuric sulfide, calcium carbonate, right? Here A is equal to B is equal to C, and when it comes to the angles, that is alpha, beta, gamma, all three equal to 90 degrees, right? So next comes monoclinic. So when I write the monoclinic Bravais lattices, so what should you remember? Example is sulfur, yes, polonium, yeah. Now here alpha is equal to gamma is equal to 90 degrees and beta is not equal to 90 degrees, right students? So it is again primitive type of Bravais lattice. Last is the triclinic. So in triclinic, potassium chromate, boric acid is one example. Here A is not equal to B is not equal to C, and alpha is not equal to beta, which is not equal to gamma to 90 degrees. So these are the 7 Bravais systems which we have. The bond parameters means the edge lengths also are given, or the angles between the edges also are given, alpha, beta and gamma. So 1, 2, 3, 4, 5, 6, 7. I repeat the examples again for your students. Cubic, you can take the example of sodium chloride and polonium. Tetragonal, you can take an example of tin and titanium oxide. For orthorhombic, you can take an example of potassium nitrate and barium sulfate. For hexagonal, you can take an example of zinc oxide and carbon monoxide. For rhombohedral, you can take an example of calcium carbonate. Done. For monoclinic, you can take an example of polonium and monoclinic sulfur, sodium sulfate. For triclinic, you can take an example of potassium dichromate as well as boric acid. Done? Yes. Now when it comes to centered, here it's again of 3 types. One is BCC, one is FCC, one is ECC. So in BCC, what you should remember, basically one particle is at the body center and at its corners. In face centered, one particle at the center of each face and its corners. Means here you have at the body center and the corners. In face centered, you have one particle in the center of each face as well as corner, and in end centered, one particle at the center of any 2 opposite faces, up and down. Suppose if I take this one, if I have to draw like this, in end centered, you will have one opposite here, one more like that. So in BCC, when I have to speak about, right students, so remember the number of particles in each, in BCC, FCC and ECC is what you have to remember. Right. So now let us see the centered unit cell. As I said, there are 3 varieties, that is BCC, FCC and ECC. So BCC stands for body centered cubic lattice, face centered cubic lattice as well as end centered cubic lattice, right? So here basically when I have to speak about further things, if I have to add, you can also write cubic unit cell, all these unit cells in these. Further I can also write simplest unit cell is one more category. You can also write HCP, hexagonal packing also, so HCP. So let us see the important thing which you have to remember. So here when I have to speak BCC, you need to remember 2 things. That is, in BCC what happens, so basically in BCC the atoms, as I said, one particle at the body center and all the corners. So here the coordination number for BCC is 8 and the number of atoms number is 2. Coordination is 8, number of atoms is 2. In face centered, the coordination number is 12 and the number of atoms are 4. In ECC, the number of atoms is 2. Right. In simplest unit cell, the coordination number is 6 as well as the number of atoms is 1. When I have to speak about HCP, the coordination number here is 12 and the number of atoms here is 6 per unit cell. Hope this is clear, students. Done. So this is the classification of the solids, crystalline and amorphous, both we have written, and after that we have seen the crystal lattice, in which the smallest unit is a unit cell. Unit cell is again, we are going to calculate the density of it. Further, unit cell is again divided into primitive and centered. Primitive is again divided into 7 Bravais lattices, and center is divided into BCC, FCC, ECC, and 2 more I have mentioned down. Now let us see the next part of the mind mapping. When I have to speak about solid state, same thing. Packing efficiency is where you have to remember, and next would be voids. So these 2 topics I have taken in one sheet. So when I have to speak about the packing efficiency, let us see the types. You have SCP, square close packing, HCP, hexagonal, then you have CCP, yes, and you also have BCC. Here the arrangement of the atoms, when I have to take the square packing, so you have AAA type, which will be repeated. So AA type would be this. What is the packing efficiency here? It is nothing but 52.4%. Correct? Here the example is polonium. When I have to take the HCP packing, here the packing is AB type. AB type. So here the packing efficiency of the percentage is 74%. So zinc is one of the best example. When I have to speak about CCP, here the packing is ABC type of packing. ABC type of packing, where the packing efficiency is again 74%. If I have to take an example, silver, copper is the best example. When I have to speak about BCC packing, here it's nothing but square close packing. So in BCC the type of packing is square close packing. What is the packing efficiency here? 68% is the packing efficiency. So example is lithium and sodium. Done, students? Now when I have to speak about voids, what are voids? Basically the gaps in between, isn't it? Right. So voids are, again, when I have to study clearly, if I have to see the definition, we have to write, these are the empty space between spheres. Let us write that. Voids are empty space between spheres. Correct? Yes. So now these voids are further divided into how many varieties? First would be the trigonal type of void. Next would be tetrahedral type of void. Tetrahedral type of void. Next category would be octahedral type of void. So trigonal type of void, what will happen here? Tri means 3. 3 spheres are in contact. Correct? So let us write 3 spheres are in contact. 3 spheres are in contact. Okay? Trigonal. Here contact. Here what is the radius ranging between? It's going to range between, in trigonal, 0.155 to 0.225 in trigonal. So when it comes to tetrahedral, here tetra means 4. 4 spheres are in contact. 4 spheres are in contact. So here what is the radius range? It is nothing between 0.225 to 0.414. When it comes to octahedral, as the name suggests, octa 6. So 6 spheres, in chemistry we call octa 6, isn't it? 6 spheres at the vertices of the octahedron. When you take the octahedron, I did a video also for this. So there are 6 spheres present. What is the radius here? It ranges between 0.414 to 0.732. Right, students? So this is clear, I think. So solid state packing efficiency, you need to remember this, and the type also, as well as voids, that is the empty spaces, which are divided into trigonal, tetrahedral and octahedral. Again further you need to remember the range. Right. So after this study, let us come back to next important concept of the solid state. You have to remember, that is the magnetic property as well as the electrical property. Right, students? Then we will do the defects. Right. So when I have to speak about the electrical property of solids, so basically electrical properties, we are going to study under 3 categories. That is, first category is the conductors, next category is the insulators, next category is the semiconductors. Correct, students? Yes. So electrical property, we are further going to study under 3 categories. As I said, conductors, insulators and semiconductors. So again, further semiconductors are again classified into, as I have written one more classification here, The semiconductors are again divided into N-type semiconductors as well as P-type semiconductors. Done. So where we have to, what should we remember in conductors? So basically conductors are those substances, important thing in this. You have two bands, isn't it? One is the conduction band and the valence band. So in conductors, what is important? The overlapping or the gap between conduction and the valence band is very small. So let us write gap between conduction band and valence band is very small. If I have to take the examples of the conductors, aluminium wires, aluminium basically, yes, so it conducts current, that's why we are using it in the form of wires. Copper, yes. So when I have to speak about insulators, the same concept, the gap between the conduction and the valence band, this is very small. This is a bit, means the gap, you can observe it clearly in insulators between the conduction band and valence band. Gap between conduction band and valence band. When I have to take the examples of insulators, clay, best example is clay, I believe I can give. Yes. Next comes semiconductors. So what are semiconductors? Basically there is very large gap compared to this, very large gap between conduction band CB and valence band VB. So silicon and germanium, we remember group 13, 14, 15, we start doping them, then we get two varieties of semiconductors. So in N-type semiconductors, that is nothing but the negative charge, in this case negative charge, and in P-type positive charge. Yes students, right? So here in the negative charge, so how does it look? One atom, gap, electrons, gap, electrons. So in this way, if it is drawn in this sequence, so arsenic in the center. So I did one detailed video about this also. You can watch the P-type and N-type. Now when I take the positive charge, so arsenic here, we are doped in where? In P-type, electron, okay. Boron, I have, boron, yes. So boron, you very well know what is atomic number? 5. So 13th group, and this is the 15th group which we are doping it. So for clear understanding, please watch the P-type and N-type video in World of Chemistry. It is available there. Next comes the magnetic properties. So when we are studying magnetic properties, we are going to study under 5 different categories. That is paramagnetic behavior of that is one of the category of magnetism. Next would be diamagnetic in nature. Next would be ferromagnetic in nature. Next would be antiferromagnetic in nature. Next would be ferrimagnetic in nature. Ferrimagnetic in nature. Magnetic. So when I have to speak about paramagnetic, let me give you the definitions. You can note, students. So paramagnetic means weakly attracted. Means unpaired electrons here. So important thing is it is weakly attracted, and what you have? Unpaired electrons. In diamagnetic, weakly repelled. WR means weakly repelled. Here you have paired electrons. In ferromagnetic, strongly attracted, and all the domains are in same direction. So all will be in same direction in this way. All the domains. In ferromagnetic, domains are opposite. If two domains are up, two will be down. In this way, equal domains but opposite. In ferromagnetics, domains are unequal. Domains are unequal. Unequal means if 3 are up, 2 may be down, and 3 like that. They are unequal. So WA stands for weakly attracted. I am writing full form. WR stands for weakly repelled. SA stands for strongly attracted. Yes, students, strongly attracted. Done. So when I have to take the example of paramagnetic, oxygen is one example, copper is one example. Diamagnetic, if I have to take, all are paired electrons, where I can take an example of water. So when I have to speak about ferromagnetic, where all the domains are in one direction, the same direction, iron is example, strongly attracted. So when it comes to antiferromagnetic, as I said, the domains are in the opposite direction, they're equal. Manganese, MnO, manganese oxide is the best example. So when I take ferrimagnetic, domains are not equal, I said. Fe3O4 is the best example. Fe3O4 is an example. Right, students? So this is about your electrical property as well as magnetic property. Now let's come back and do the last, that is the defects of solids. Very important topic. So when I have to start with the defects or the imperfections of solids, well, how many types of defects we have? We have both the point defects as well as line defects. Yes, students? Yes. So when I have to speak about the point defects, point defects means where you will find the defect at one point. Means basically we are talking about at a point. Line defects are what? They are going to show it in entire row. Done. So point defects are further they are classified, means they are also called as stoichiometric, means stoichiometric defect means they will not disturb, they will disturb, both are there. So we'll speak in terms of stoichiometry. Stoichiometry, the exact ratio of this. So if they disturb, suppose if the stoichiometry ratio, if there is imbalance in the ratio of the crystal lattice, if it disturbs, there are again two varieties. If the stoichiometry does not disturb, so stoichio STOI CHOMETRAC, stoichiometry. If the stoichiometry do not, then the type of vacancy is called, the type of defect is called vacancy defect. Vacancy defect. Once again, if the stoichiometric ratio, if it does not get disturbed, then it is called vacancy defect. So only the lattice sites will be vacant. Here in vacancy defect, only the lattice sites will be vacant. So in what it is observed? It is observed in ionic solids. So only the vacancy will be created in the lattice sites, or the vacant lattices will be there. Suppose if the stoichiometry is disturbed, then here do not disturb is vacancy. This I have written. If the stoichiometry is disturbed, then you have to remember it is an interstitial defect. Interstitial defect. So here what is happening? Here we said only the vacancy is created in the lattice sites. But here in the interstitial defect, the particles whatever are there in the lattice side, they'll go and occupy in the interstitial space. Means when it is fixed like this, one of the particle will go and occupy the interstitial space. So this is also observed in non-ionic solids. So remember students, stoichiometry, again we have stoichiometry not disturbed is vacancy, stoichiometry disturbed is interstitial. Now let us come back to line defect. So line defects, here we said there is a defect in the entire row. Again these are classified into two varieties: non-stoichiometric, this is non-stoichiometric defect, and this is the impurity defect. impurity defect. So when I have to speak about the non-stoichiometric defect, it is again of two types. What do they do in non-stoichiometry? They disturb the stoichiometry. Basically, non-stoichiometry means they disturb the stoichiometry. It is again of two varieties, that is metal excess defect and metal deficiency defect. Metal excess defect and metal deficiency defect. So here in metal excess defect, what happens? Why? Due to anionic vacancy. This is why it is created, due to anionic vacancies and presence of extra cation. So let us write two keywords: due to anionic vacancy and presence of extra cation. Done. Example is zinc oxide for this metal excess defect. So in metal deficiency defect, what happens? It shows variable valencies. The best example which we take is Fe+2, Fe+3. So metal deficiency defect is due to variable valencies. Let me come back and repeat. Metal excess defect is due to anion vacancy which is created, as well as an extra cation comes and occupies its space. And in metal deficiency defect, as Fe+2 and +3, iron shows two oxidation states here, so it shows variable valency. Because of that also metal deficiency defect. Next comes impurity defect. Impurity defect are of two types. One is Frenkel defect as well as one is Schottky defect. So in Frenkel defect, what is happening here? Smaller ions are dislocated to interstitial sites, smaller ions. And here, okay, let us write smaller ions, that is the cations, are dislocated. Smaller ions are dislocated. In Schottky, what will happen? Equal number of ions are missing. Equal number of ions are missing. Right, students? So in Frenkel defect, what is the example? Zinc sulfide, silver chloride is an example. In Schottky defect, as I said, equal number, both the cation and anion. Best example, sodium chloride. Potassium chloride is an example. Right, students? So this is the complete summary of the solid state chapter from my side. Let us see what we have learned in all the papers. Let me get all the papers. Yes. So let us see the whole thing once again. So I have taught in the first page, students, this is the thing. I have taught about classification into crystalline, as well as we have studied about the crystal lattice, unit cell, primitive type and centered type. Again, in classification, I have taught you about molecular solids, ionic solids, covalent and metallic. Further classification of molecular solids. In page 2, I have taught you what is the concept of the packing efficiency, what you should remember for your exam, and voids. Right. After that, I have also taught you the solid state, that is in solid state electrical properties and magnetic properties. Here we have studied electrical properties under conductors, insulators and semiconductors. Semiconductors are again divided into N type and P type. In magnetic property, we have studied the important thing to remember: paramagnetic, diamagnetic, ferromagnetic, antiferro as well as ferri. In that, which is strictly attracted, which is strongly attractive, which is repelled, I have written here. Examples also I have given. Next, in last category, I have given the concept of the defects or the imperfections. They are classified into point defects and line defects. Again, we have given stoichiometry, where there is no stoichiometry which do not disturb. Stoichiometry is not disturbed, that is vacancy. Stoichiometry is disturbed, that is interstitial. As I also gave the definition of the interstitial also, you can watch little bit, go to the previous this one and pause and listen to it. Again, line defects are divided into non-stoichiometry, that is the disturbance of the stoichiometry, metal excess and metal deficiency, and impurity defect, Frenkel and Schottky. So this is the thing, students. Thank you for watching. I'll also meet you again with the next chapter, that is this time it will be one organic chapter from my side. After that, I'll be doing one physical, one organic, one inorganic. Like that, I'll be doing all the chapters. All the 16 chapters will be done from my side. Thank you for watching. Stay happy. I expect most of the students to watch this completely and share it with your friends. Stay happy, stay healthy. Good evening, students. Welcome to one more session of your World of Chemistry, that is your WOC. Right, I have kept in the community tab 3 things I have asked you, whether should I do the aldehydes mind map, or should I do the redox reactions, or should I start with the grade 10 topic, right? So because I know your days are very less, intensity of preparation is more. Aldehydes, ketones and carboxylic acid chapter is the most requested mind map, so I have decided to do it for you all students. See, end of the day, your studies are important and you are important for me, isn't it? Right. So in aldehydes, ketones and carboxylic acids, first I have taken the whole chapter and I have done a complete analysis of the topic, and I'm going to present it in front of you. So what is special in this? As I said, in this chapter, 2 things you need to remember. What is similar, what is different, where you're going to use a reagent. Ultimately the product is important, isn't it? Reagent is important, reactant, reagent, as well as the product is important. First, let us analyze how are we going to study the whole mind map of aldehydes, ketones. Maximum, I have to tell you, I'll upload in 2 videos. The first video will cover all the physical, preparations as well as chemical properties, and the second video will include the structure and name reactions. So completely I'll be doing the first video, watch it carefully, and I also request you to watch the second video, right? So here, when I come to the first part, that is preparations. So basically what we have in the chapter, we are supposed to learn the preparations of aldehydes, aromatic aldehydes, ketones, aromatic ketones, acids and aromatic acids, isn't it? Yes. So right now, what are these? These are the reactants from which we are going to prepare. First, I listed out. I have just put a tick what is required, and then I'll give you a detailed explanation. Right. So when I see aldehydes, just see, we can prepare aldehydes from acyl chlorides. Yes, we can also prepare aldehydes from aromatic, means we can prepare aromatic aldehydes from acyl chloride. So acyl chloride is a reactant. I can prepare aldehydes, aromatic aldehydes, ketones, aromatic ketones, no. Acids, aromatic acids, no. Done. When it comes to the nitriles, I'm going to prepare nitriles from nitriles, aldehydes and ketones and acids. So aromatic ketones, aromatic aldehydes, aromatic acids are not prepared. Why did I do this? Because this is how in the exam you should not get confused. When this is given, okay, acyl chloride will prepare what? 1, 2, 3 and 4. Like that you need to remember. Right. Next comes esters. From the esters, I can prepare aldehydes and acids. Both I can prepare. Done. Next, when it comes to toluene or methylbenzene, I can prepare, see, aromatic aldehyde, because this is an aromatic compound. I can prepare aromatic aldehyde as well as aromatic acids also. But important, I can also prepare acids also from that. Let us see how I can make it. So in toluene, options 1, 2, 3 are open for us. We will learn what it is. Then comes benzene. Benzene, again aromatic compound. I can prepare aromatic aldehyde as well as aromatic ketone. I think little bit understanding you have got. First, whatever you study, you need to understand where I can apply that particular reactant. So note this table. These are the things. Now let us come back and do the next part. Right. The next part of the preparation, that is, we'll see now Grignard's reagent we have taken. Let us see, can we prepare? Yeah, no, acids only. I'll use the carbon dioxide there, where I'll prepare the carboxylic acid group. So Grignard's reagent, I'll be using it for preparing acids only. Done. Next comes alkenes. I'll be using alkenes to prepare aldehydes and ketones. I'll show you, as I said, I'll show you the detailed reaction of the preparation of the aldehydes and ketones in a different way. Please watch the video till the end. Then comes your alkynes. So from alkynes, I can prepare aldehydes and ketones. Okay, don't worry students, simple it is. Actually, this table will be very useful for you. How? I'll tell you. When you learn the reaction, you can come back. Okay, Grignard's reagent, write the reaction. Aromatic aldehyde, not there. Ketone, not there. Aromatic ketone, not there. Acids, it is there, write the reaction. So this table will be useful for both the cases. Let us see. Now with this, preparations are over. Now let us come and write or tabulate chemical properties of aldehydes, ketones and carboxylic acids. Right, students? So preparation, I think you have noted it. Now chemical properties. When it comes to the chemical properties, there are list of chemical properties for aldehydes, ketones and carboxylic acids. So I have combined the common aldehydes and ketones, then carboxylic acids we will do. Now when I see the reaction, just see here, very important table. Here reaction of aldehyde with HCN, yes. So HCN, sodium bisulfate, Grignard's reagent, alcohols, imines, hydroxylamine, phenyl hydrazine, reaction with semicarbazide, 2,4-DNP. Till here all the reactions are shown by aldehydes and ketones. So don't worry, as I said, I'll be showing you the detailed explanation also. So all these reactions, or the aldehydes will react with all these, ketones also will react with all these. Now here this is where is important for you all. Now when it comes to tolerance test, remember tolerance test is given by aldehydes and it is not given by ketones. That is a differentiating test for aldehydes and ketones. But what type of ketone gives tolerance test? If they are alpha hydroxy ketone. What is alpha hydroxy ketone? I'll also show you that, right? So if they have a alpha hydrogen in that beside the ketone group, so alpha hydroxy ketone, they will only show tolerance test. Done. Here when it comes to the fillings, aldehydes will show, when you add fillings A and fillings B, it will show, it will respond to that. But here ketones will not respond. But which ketone will respond? Methyl ketones only will respond. Remember that. Okay, here I'm talking about a haloform reaction. Okay, let us come back. Fillings, aldehydes will show, ketones will not show fillings test. Remember that. When it comes to haloform test, aldehydes will not respond to haloform, but ketones, which ketone will respond? Methyl ketone will respond. Here I said it is alpha hydroxy ketone will respond. Here methyl ketone only will respond to haloform reaction. So these are the list of chemical reactions. There are few more. Let us come and write first. Right, students, after those reactions, let us see these. So apart from that, we also have very important name reactions, that is aldol condensation, cross aldol condensation, Claisen-Sidbed reaction, as well as Cannizzaro reaction. Now remember, aldol condensation, both aldehydes and ketones we can show that aldol condensation, they respond to that. Cross aldol is shown by aldehydes. Remember that. When it comes to Claisen-Sidbed reaction, we call this when we mix an aldehyde and a ketone. Just for your understanding, so whenever there is Claisen-Sidbed reaction, you will be mixing an aldehyde group as well as a ketonic group. Done. Next comes the Cannizzaro reaction. For all these, I have done a detailed video which is kept in the playlist. Very clearly I have explained the mechanisms, because this is a mind map. I'm just giving you an idea, right? So in Cannizzaro reaction, basically, Cannizzaro reaction is responded by compounds which do not have alpha hydrogen. For example, formaldehyde, benzaldehyde, example. Right. Now here, this is the chemical properties of the carboxylic acids. 1, 2, 3, 4, 5, 6, 7. Simple 7. It's easy. Now we are going to show the reaction of acid with alcohol. That's nothing but esterification reaction. Done. I'll be showing this one, reaction with PCl3, PCl5, SOCl2, that is thionyl chloride. I'll be showing the decarboxylation reaction, then reduction, as well as halogenation of alpha hydrogen. Now at last but not the least, we have reactions of the aromatic acids, that is ring substitution reactions. So I think it's easy, isn't it? Preparations to 1 page, chemical properties 1 page, over. Now what is the speciality? When you're learning, when you're learning from this video, when you see basically the tabular column will have a complete understanding. See here, it will be divided like this: aldehydes, ketones, acids. Now suppose if it is acyl chloride, now acyl chloride, how it will respond, how aldehydes, what is the reaction, ketones, what, acids, one. At one shot you will get the whole idea. So let us come back and note. Now I think you have a basic idea of what are the preparations and chemical properties. Now let us come and start with the first thing, that is preparations, and that too will be doing in this way. So comparative study, aldehydes, ketones, acids, at once you will understand. So let's come and start with those. Right, students, welcome back. Now we have written already the tabular column. Now let us see, as I said, we have different columns, isn't it? Right. So here, what did I do? I have taken the common reactions which are there, right? So here, these are the preparations. So with the common reactions which are there for aldehydes, ketones and acids. So what did I give in the tabular column? I said we can prepare aldehydes from acyl chlorides, ketones from acyl chlorides, as well as acids from acyl chlorides. Correct? Yes. Now what actually are acyl chlorides? Let us see. Here one more thing is we can also prepare the aromatic aldehydes, that is like benzaldehyde, right? So for benzaldehyde you will be taking benzoyl chloride. Let's see. So here acyl halides, I'm going to prepare aromatic halide, nothing. You're going to take the benzene ring. So acyl group is nothing but COCl, right? So here what are you going to do? Here this process is nothing but the reduction process, that is addition of hydrogen. You'll be adding hydrogen to this, in which presence? In the presence of lead and barium sulfate. So what product do you get? So reduction we said, isn't it? So HCl will come out, right? HCl will come out, and what you will get? CHO. So HCl out and CHO. So what product do you get? You will be getting a product called benzaldehyde, CHO, and HCl is out. So what is the type of reaction called? This is called Rosenman reduction reaction. Simple, students, this is called Rosenman reduction reaction. Right. So here this is one. Now suppose if I have to take the same ketones in acyl group, right? Here I'll be taking RCOCl. So here I took aromatic acyl chloride, I got aromatic aldehyde, that is benzaldehyde. Here I'm going to take aliphatic acyl chloride, that is RCOCl. But here what is important for in case of ketones, dialkyl cadmium is what you're going to take. Right, so because this dialkyl cadmium is going to introduce this alkyl group into this, and cadmium chloride is out. Let us see the reaction. What happens is, now if I take 2 moles of this, okay, right, 2 R prime C double bond O, R goes in, and plus cadmium chloride. This is done, students. This is over. Now when it comes to the acids, right? So acids, acyl chloride, if I have to take, again I'm going to take an aliphatic RCOCl. Here there are 2 things. First, as I said, it can means you can do the hydrolysis part of this. This is done. When you do the hydrolysis part, and one more, you can do the complete hydrolysis as well as partial hydrolysis also. So what product you get? You're going to get a product when you do RCOH, and what is left out? Cl minus. In this case, when you do, you will be getting RCOO minus, and further and hydrolysis, further more and more you do hydrolysis, then you will get a required acid. This is clear, students? So here what is the thing? Here when you study an acyl chloride, you have a clear understanding among these 3. So this is aldehydes preparation, there is aromatic aldehydes, this is ketone preparation, this is acid preparations, complete and partial hydrolysis. Right, now let us come to the next one. Now as I said, here we are going to prepare, and that is a common preparation from nitriles, right? This is the second thing which we have written, isn't it? So in the nitriles part, when we do, I said we can prepare from nitriles. Let me put the paper little bit down. Okay, so from the nitriles I can prepare aldehydes. So let us see what are nitriles actually. Right, so C triple bond N is nothing but nitrile. Okay, so what am I going to do? For here, in this case of aldehydes, first I'll be taking, important thing, this we do it using stannous chloride, that is SCl4. This is very important reaction, right? So SCl4, what happens? First of all, SCl2 combines with HCl. This is fine. When it combines, it's going to form what? It's going to get converted to SCl4 plus 2 hydrogens are released, right? So 2 and 2, done. Here, important thing, these 2 hydrogens, whatever are there, this is where we are going to use it for reduction, right? So now I'm going to take the required nitrile, R C triple bond N. To this is used. These 2 hydrogens will add up, and the presence of HCl, what do I get? I am going to get a compound. This bond breaks in between these 2, and RCH double bond NH dot HCl. Further, if you take boiling water, so further you're introducing boiling water, and then what happens, this ammonium chloride is there, no? NH4Cl comes out, and the leftover NH4, first I'll write off NH4Cl, and what is left out, RCH over the boiling water part, RCHO. See, here I'm just writing the reaction, students. Clear explanation I have given in the earlier videos, please watch it. Done. So when it comes to the ketones, remember ketone from nitriles, here I'm going to use, let us take this ketone, ethyl nitrile, done, right? Here I'm going to use C2H5 MgBr. Remember, here what did we use? We have used stannous chloride. Here we are going to use the Grignard's reagent, RMGX, right? So when it is Grignard's reagent, compulsory you need to use ether, isn't it? So what happens, the bond is going to break here, and you're going to get a compound, right? So here the bond has broken, and here also there is a cleavage of the bond, right? N is here only, and when there is a cleavage of the bond, MgBr comes and adds here, right? So now what is left out? C2H5. This is done, students. Now this one you will go do further hydrolysis. When you do further hydrolysis, what happens? This compound, just see here, this is nothing but HOH, isn't it? So OH comes out with magnesium, and the hydrogen whatever is there, it goes and adds. What product I get? I get C2H5. I'm combining both of these, and carbon is here only, double bond oxygen, because HOH is there, right? So the double bond oxygen and C2H5. What is this? This is called propiophenone, correct? Right? So right, students, so this is clear, I think. So both the compounds, hydrolysis, this is the compound, right? And next thing, if I have to do the if I have to prepare acids from nitriles, what is the procedure? I'm going to take nitriles, done. You're going to do the hydrolysis part of this, H or OH minus, done. What do I get? Again the bond is going to break here, right? And I'll be getting R, C, and H2, okay. This one further on hydrolysis or heating, what do I get? Okay, RCOOH. What did I do? Let me see. First one, okay, little, I think small change in this, little bit. Let me adjust my lens. Okay, right. So here what did we say? Here we said, okay, RCOH. Now what will happen to this? This comes out as ammonia gas. This is what you need to remember, right, students? This is clear. So the from nitriles, for aldehydes you need to take stannous chloride, then for ketones you need to take Grignard's reagent, and here you will be doing the hydrolysis part, right? So let us do the next part of the reaction, right? What is this? This is from esters, remember. So esters reaction, I think I have seen one question also in your NEET and NEET examination. So carefully, students, just observe carefully, right? So here as I can prepare aldehydes from esters using which one? Dibal, and in this case you will be doing acidic hydrolysis. Let us write that. So here what you're going to do, let us take one ester. So a longer chain hydrocarbon we will take, CH2, taken dine, the double bond O, C2H5. So this is the ester. Now what am I going to do? I'm going to introduce Dibal to this, diisobutyl aluminum hydride. So what will happen? This gets reduced. When this gets reduced, what will happen? The S2 group, whatever is there here, right? So here this gets reduced and this is pulled out, and the product which you get is 9 C double bond OH. So this reaction, remember, the conversion of esters to aldehydes, you can do it using Dibal, right? So here esters, from esters I can't prepare ketones, so I am putting a dash. This is which is important. Now in case of acids, suppose if I'm going to take an acid, both aliphatic and aromatic, let us take. So first I'll take an ester, right? So what am I going to do? I'm going to do, right, okay, let us take, this is a reversible reaction. So right, H in the presence of H3O plus, what am I going to do? I'm going to do acidic hydrolysis. This arrow should be like this, not like this. I just wrote it. So acidic hydrolysis. When you do acidic hydrolysis, there is a cleavage of the bond here at COOH, and what do you get? You get an acid, that is benzoic acid, and what is left out? ethanol is left out. C2H5OH is left out. That's fine, students. Suppose if I'm taking an aliphatic aldehyde, let us take the aliphatic ester. So I'm taking an aliphatic ester, COO, C2H5. Here, what am I going to do? I'm going to introduce sodium hydroxide. What is the name of this reaction? This is nothing but ethyl butanoate. Correct? Yes. Ethyl 1, 2, 3, 4 ethyl butanoate. So what will I get? I'll be getting a product that is a sodium salt of that. Okay, Na plus there's a cleavage of the bond here. You get C2H5OH. Now further on hydrolysis of this H3O plus and hydrolysis, I'll be getting the required acid. So 1, 2, 3, 4. So 1, 2, 3, 4. So this is an acid, right, students? This is clear, I think. So we have got, or we have prepared aldehydes, we have prepared acids, but ketones are not prepared using esters. This is clear, right? Now let us come and see the next part according to yours, that is from toluene, okay, or the methyl benzene. Here I'll be preparing aromatic aldehyde and aromatic acid from toluene. Why? Because this is an aromatic compound, isn't it? Right. So now when I take aromatic aldehyde, just see here. So I'm going to take toluene. So what you should remember, so toluene here, you will be doing two types of reactions using chromyl chloride, right? So you will be using chromyl chloride here, carbon tetrachloride. What is the role of chromyl chloride? I have explained in the video. I'm just giving you the reactions here. Please watch the earlier videos. So here I'm going to take 2 moles of chromyl chloride. So there is a cleavage of the bond here. What do you get? You will be getting the benzene ring with CH and chromyl chloride. This is how it attaches. Again, I'm telling you, students, I have done a detailed video about all these. This is only for the quick revision for you all. That's why I'm just explaining here. Further, this compound is taken and it is allowed to undergo hydrolysis, where I'll be getting the final product, that is benzaldehyde. Done. Now, next, further, I can also prepare benzaldehyde by using CrO3 and 0 to 10 degrees centigrade, and in the presence of acetic anhydride. This is one more option which you can use. So again, there is a cleavage of the bond here. What do I get? The first product which I get, just like an intermediate product, I get CHO, CO, CH3 taken twice. Further, this undergoes hydrolysis, right? H3O plus hydrolysis, you will be getting benzaldehyde, right? Benzaldehyde. This is clear, students, right? So this is how. Let me take my scale and divide this page so that it's not confusing you all. Okay, so aromatic aldehydes I have prepared using chromyl chloride. I think you have understood this, right? Right. Again, I'm saying, students, I'm specifying, please go to the detailed explanation of the videos which I did here. This is just for revision. Now I'm going to convert toluene to aromatic acid. So again, I'm going to take toluene. Here also 3 things. Here you can use irrespective of whatever is the size of the alkyl group. Means here, let it be you take methyl, ethyl, propyl, anything, but you will get a carboxylic acid. Remember, here there are 2 methods. What? One is, here I'm going to use KMnO4, an oxidizing agent. There is an oxidation process, and I can also use NaMnO4 in the presence of sodium hydroxide. What is the role of this? What is the role of this? I have explained in the earlier videos. Please watch it. Yeah, right. So here in the oxidizing agent, I said, irrespective of the size of the alkyl group, you will be getting acid only. Whatever is the size, you will be getting acid. Here, first you will be getting an intermediate product, right? Sodium salt of that, CONA plus. So what do? You will acidify this. You will acidify this with H plus. So acidify with H plus. H plus. Then what happens? Finally, this is getting converted to benzoic acid. So whatever, and Na plus is out. So irrespective of the size or the chain size or the alkyl group, you will get the acid only. Right. Right, students. Now let us see the preparation of aromatic aldehydes and aromatic ketones from benzene. Right. So here we are going to take benzene. What are we going to do? Here I need to prepare aldehyde, correct? So you're going to introduce, or this is nothing but your free Freelicraft's alkylation, acylation sort of thing. But just let us see here what are you're going to do. You're going to introduce, let's say, chloride. Okay. You require a Lewis acid, that is aluminium chloride. When you add Lewis acid to this, benzene to benzene, you'll be getting aldehyde and HCl is out. This is fine, right? Now in the same thing, suppose if I have to just take or prepare aromatic ketone, so what am I going to do? I'm again going to take benzene, right? And here I'm going to introduce acetyl chloride group to this. Here again I'm using aluminium chloride. Now here you're going to use excess benzene and heat it to 80 degrees. What are you going to get? You're going to get COCH3 plus HCl. This is the ketone which you have, right, students? So again I'm specifying, please watch the earlier videos. Here I'm just giving you the examples only, so don't get confused and don't panic. How watch the earlier videos, you'll understand it. Now here, next thing, we are going to prepare a common preparation, that is we are going to prepare aldehyde from primary alcohol, ketones from secondary alcohols, and acids again from primary alcohols by oxidation process. Let us see. So here very important reaction, let's see. So whenever you're taking a primary alcohol, so I'm going to take a primary alcohol here. What is primary alcohol? There are 2 hydrogens and 1 alkyl group, right? So here in this case I'm going to use PCC, okay, right, pyridinium chlorochromate and Collins reagent, and you can also take copper in the presence of 573 Kelvin. Then what do you get? You're going to get aldehydes, remember, right? Now when it comes to the ketones, secondary alcohols I need to take. So in secondary alcohols, what do we say? We have in the secondary alcohol, you will be having 2 alkyl group, 1 H and OH, correct? Isn't it? Right. So here also same conditions, just like this. If you use the same reagents here also, you will be getting a ketonic group in this case. Done. When it comes to acids, I need to use primary alcohol. So first thing, I'm going to use primary alcohols, right? First, then I'm going to use an oxidizing agent, that is alkaline KMNO4, because this is oxidation, isn't it? Right? So, and hydrolysis. Then what happens? You will be getting RCOOH. Hydrogen is removed, oxygen is added, right? So here there is one more reaction to prepare acid, that is using Jones reagent, right? Let us take that. You're going to take this compound and you're going to introduce, or you introduce Jones reagent. So what is Jones reagent? It is nothing but CrO3 in the presence of sulfuric acid. So what do you get? You're going to get an acid called decanoic acid. Alcohol, this hydrogen is removed and you'll be getting the required acid COOH. This hydrogen is out and oxygen is in, right, students? So this is how you're preparing aldehydes, ketones and acids using the oxidizing agents, right? Now let us see the next one, that is catalytic hydrogenation of alcohols or dehydrogenation of alcohols. So basically catalytic hydrogenation, here nothing, simple. You need to remember you will be using a metal for this, okay? So there's a dehydrogenation of alcohols. In the exam paper, if they give you in this way, that is copper at 300 degrees centigrade, okay, right? So this is your catalyst which you are using. This is the temperature. Dehydrogenation means you are going to remove hydrogen, right? Suppose if you are taking a primary alcohol like this, CH2OH, right? Primary alcohols, done. Here what happens? You need to remove hydrogen, isn't it? So you need to remove hydrogen and add oxygen? No. But here we are preparing aldehydes. So you are going to just remove hydrogen. You will be getting CH3CHO. there is one more. Suppose if you are taking secondary alcohols also, same thing I'll be taking. Here you are going to remove this hydrogen. So what am I going to use? I'm going to use a catalyst for this. Remove hydrogen. What do I get? I'm going to take out this hydrogen and this hydrogen, this hydrogen and this hydrogen. What will I be left with? See, ketone. See here. So simple, isn't it? I have prepared this one aldehyde and ketone using copper at this temperature, that is 300 degrees centigrade. Both the things are clear, students? Done. Now let us see one more. Now next important thing, we are going to prepare your ketones and acids using ozonolysis process, that is addition of ozone. Let's see. Here I'm going to take an alkene, right? So H3, I'm going to take an alkene. This is also there. Hydrogen. So this is an alkene, correct? And CH3. Now in the ozonolysis process, you are going to introduce O3. O3 adds, and the first important thing, next, usage of hydrogen peroxide. I did a video also for this. What is the role of hydrogen peroxide here? Why are we using this? When you add this, the double bond breaks and oxygen adds, then one oxygen above, two oxygens below, ozonide is formed. So I'm directly writing the product here. As I said, please watch the earlier videos. I did very clearly what actually are the compounds, what is the product form. So here in ozonolysis, I'll be getting a ketone and a mixture of acid also. Mixture of acid, COH. So this is the ozonolysis process, a mixture of acid and ketone. Right. Now suppose, let us take one more example. Suppose if there is an alkene like this. This is an alkene, okay, with alkyl groups, right? Now you are going to add oxygen, ozone to this. I'll be explaining a little bit lengthy, right? R, C, this is there, R. Now the bond breaks here, one oxygen adds above, one more carbon, one oxygen here, one more oxygen here, and R prime and H. This is ozonoid. This one, what are we going to do? We are further going to take it and do the hydrolysis part, H2O hydrolysis part, right? So what are you going to get? There is a cleavage of the bond here. In this way it cleaves, and you will be getting presence of zinc also. You will be getting two products. One is ketone and one is aldehyde. So the ketone, if I break it here, the ketone which I get is C double bond OR, and this side if I break, this part if I break, the compound which I get is C, R and H. So this is the ketonic part and this is the aldehydic part, right students? This is clear, right? Now let us come and see the next part, that is preparation using hydration of alkynes. So I think with this almost over, we'll be coming to the chemical properties, right? So when it comes to the preparation or the hydration of alkynes, so what are we going to do? Remember, whenever you're seeing alkynes, the most important thing, this occurs in the presence of mercuric sulfate and sulfuric acid, HgSO4 and H2SO4, right? So here I'm going to write the reaction. First take an alkyne. Done. You're going to do the hydrolysis part of this. What are you going to do? You're going to take in the presence of Hg plus 2 and H plus what? 333 Kelvin, right? So what are you going to get? The first important thing, there is a cleavage of the bond here and hydrogen adds here. It becomes double bond. Okay, this is OH. Further, this undergoes isomerism. This undergoes isomerism and it forms CH3, the shifts here, and C double bond OH. Simple, right? Now here let us take this. Now in propine also, I'm going to take propine and then convert it to propanone. I took ethine, I converted it to ethanol. Now I'm going to take propine and convert it into propanone. Same thing, initially you're going to take propine. Then you need to do hydrolysis. What are you going to do? You need to add Hg plus 2 and H plus sulfuric acid. What temperature? 333 Kelvin. As I said, the bond breaks and you're going to get a compound E double bond CH2, H adds there, H adds here, OH adds here. Done. This further undergoes isomerism and what do you get? This bond is going to shift here. this H is going to shift here. You're going to get CH3, C double bond O, CH3. This is fine, students. I think this is clear. Hydration of alkynes. Now, preparations of aldehydes, ketones, acids are over. Now, let us come and see the chemical properties of acids, chemical properties of aldehydes in a very different and unique way. Right, students, after the preparations, let's come and see the chemical properties of aldehydes, ketones and acids. Right, as I said, important thing. Let us learn the chemical properties in a different way. See here. Here, when you see the chemical properties, basically, if I have to take an aldehyde, okay, let us take. Now here, this is an aldehyde with an alkyl group, done. Here in the chemical properties, there is nothing but the nucleophilic addition as well as the nucleophilic addition elimination reactions will happen. Let's see. Here I'm going to add a nucleophile to this. Done. Right? Fine. Nu is a nucleophile. Now what happens here? There is a cleavage of the bond between the carbon and oxygen. Right? What type of compound you get? You get R. This is here. C, H and the nucleophile and OH. This is a compound, right, students? So here what happened? Here the nucleophile, there is a cleavage of the bond here, right? Exactly. Hydrogen got added to the oxygen and nucleophile got added to the carbon, right? So the list of reactions for aldehydes, where we'll be writing the reaction. Which one? What is the name of the reaction? We'll be writing what is a nucleophile and what is a product, right? So the first thing, when we take the first reaction is the addition reaction. What are we adding? We are going to add hydrogen cyanide. In this case, what is a nucleophile which we have? We have Cn minus is a nucleophile, right? What product do you get? Exactly the same procedure. Wherever there is nucleophile, you're going to add this. So you're going to get R, C, OH, and the nucleophile place is Cn and this is H. What is the name of this compound? Cyanohydrin, right? The next type of reaction, again we're going to do an addition reaction. Here I'll be adding sodium bisulfate, right? Here what is a nucleophile? This is the nucleophile. This is the nucleophile. Where are we going to add product? Same thing, R, C, H, OH. In the nucleophile place, you're going to add SO2Na. What is the name of this? This is nothing but the addition product of or addition of sodium bisulfite, right? Or adduct of bisulfite. The next thing, here I'll be doing one more, that is one more addition product. Here I'll be adding alcohol. In alcohol, what is a nucleophile? OH is a nucleophile. Understand this. Now what do you get? Product R, right? C, OR, right? Then H and OH, right? Because here there's a cleavage of the bond and oxygen, there is cleavage exactly here. OH adds to the above and R adds to the end, right? The next thing, let us take one more reaction. Here I'll be adding Grignard's reagent. Grignard's reagent, let me move the paper a little bit down, right? So here the addition is for Grignard's reagent. So in Grignard's reagent or Grignard's reaction, what is the Grignard reagent? RMgX. In Grignard's reagent, what is a nucleophile? Alkyl group, electron donating. The product would be same, R, C, H, OH and R. This is fine, students. So exactly the first step, whatever is there, the first step if you follow, you will clearly understand what is the concept. And next thing, let us come and add one more addition of organolithium. So one more thing is addition of organolithium, right? So organolithium is nothing but RLi. In this, what is a nucleophile? Again, it is an alkyl group. So what product do you get? You're going to write R, CH, OH and nucleophile place R. Simple, isn't it? Right. Now next, let us write or add hydroxylamine. The next type of addition is hydroxylamine. So hydroxylamine. Hydroxylamine, what is the formula? NH2N, H2OH. Here, what is a nucleophile? OH is a nucleophile, correct? What product do I get? R, C. Okay, let me write here, or let us take, right, no problem. Here C is there, the aldehyde group. To that, let me write the carbonyl group first. Carbonyl group is 1 and NOH, oxime we get. Suppose if I take hydrazine, what is the formula? NH2, NH2. What is the nucleophile here? NH2. So what product do I get? I'll be getting hydrazone. This is hydrazone. Here students, I'm just writing this one. For the clear explanation, you can watch the video which is there in the playlist, right? Next, after that, suppose if I have to add phenylhydrazine. What is the formula? Phenylhydrazine formula is C6H5 NH2 NH C6H5. Correct. Now when I have to add, or the product formed is nothing but double bond NH C6H5. This is phenylhydrazone. Correct. And next one more is there for you all, that is nothing but semicarbazide. Next one is semicarbazide. So in semicarbazide, what is the formula? NH2 NH C double bond O NH2. When this is added to the carbonyl group, what product I get? I'll be getting a product something like this. This is called semicarbazone, right? The next we have 2,4-DNP. So I'll be adding 2,4-DNP to the carbonyl group. What is 2,4-DNP? It's nothing but NH2 NH. You have the benzene ring, add it, one nitro group at the whole, say 2 position, one nitro group, 4th position, one more nitro group. What product do you get? You will be getting a compound something like this. Okay, again NO2, 2nd position NO2. What is this called? This is called 2,4-diphenylhydrazone. Right, so let us recollect once again. This is nothing but oxime, this is nothing but hydrazone, this is nothing but phenylhydrazone, this is nothing but your semicarbazone, and this is nothing but 2,4-diphenylhydrazone. Right, let us come and do the reactions. Now I think it is easy students. Let me take out this page. 2 pages are over. I have done the chemical reactions of aldehydes in a very simple way. Just see, very easy. Right, now let us come and do the chemical properties of acids. Here acids, as we said, we are going to learn in the form of a mind map. Right, so here in acids, remember, let me take my page straight. Okay, done. Here there are 2 varieties or 3 varieties of reactions where you will be seeing, suppose if I take RCOOH in the acid group. So here you will be seeing reactions where there is cleavage of carbon and oxygen. You will be seeing reactions where there is cleavage of oxygen and hydrogen. You will be seeing reactions where there is cleavage of complete this bond, right? Let us see. Now I'll be writing the list of reactions. So acids, first of all, when you introduce a sodium, so here it's going to form a compound that is nothing but RCOONA and hydrogen gas is released, right? So further, if you just take it, it will get converted, means the acid first forms the sodium salt and hydrogen gas is released with a metal, right? Suppose if you're taking sodium hydroxide, right? So sodium hydroxide is the same thing, same product, sodium salt, and here with sodium hydroxide you will get water. Suppose if I am introducing sodium bicarbonate, again I'll be getting sodium salt, and along with this carbonate is there, so carbon dioxide is out, water, this is there. So all the 3 products are same, but with the metal you get hydrogen gas. With sodium hydroxide you get water. With sodium bicarbonate you will be getting carbon dioxide gas. Remember that. Now suppose if you are taking, or these are the cleavages of which bond? Here there is a cleavage. If I take RCOOH, here there is a cleavage of the OH bond. That's why, because there is a cleavage of the bond, sodium came and attacked here. Done. Suppose here I am introducing thionyl chloride. Now from here the bond or the type of bond is cleavage of RCOH bond. Here there is a cleavage. Here it was cleavage before the hydrogen. Here there is a cleavage before oxygen. Now when I introduce thionyl chloride, I'll be getting RCOCl, we very well know sulfur dioxide gas comes out and HCl. Now, next thing, if I am introducing or in the presence of lithium aluminum hydride reducing agent or ether I'll be using, right, and hydrolysis, then I'll be getting an alcohol or CH2OH. Acids on reduction gives alcohol, isn't it? Right. Now, next case. Suppose if I have to show you the esterification reaction, which is a reversible reaction. Esterification reversible. So, to this acid, I am going to add alcohol. What do you get? Acid plus alcohol gives me ester plus water. What is required here? You require sulfuric acid, dehydrating agent. Further, if I have to take the reactions, I'll be doing one decarboxylation reaction. For that, what do you require? You require sodium hydroxide and calcium oxide. So, this takes out the carbon dioxide, and what do you get? In the presence of sodium hydroxide and calcium oxide, you'll be getting hydrocarbon and sodium carbonate. Now further, suppose if you find in the exam ammonia is there in the reaction, right? Ammonia is there on the top of the arrow, nothing. It is again a cleavage of COH bond only. What do you get? I'll be getting a compound ammonium salt. Ammonium salt. This one, further if I do hydrolysis of this, you will be getting amide. Done, students? Right. Now, apart from this, others also there. Suppose if I take PCl5 or if you take PCl3 will take here. So, PCl5 will be giving a compound. Right, students, little small correction from my side. I'm sorry for this. So here, please take out this reaction. We have written the products wrong. In PCl3, here also we have written the products wrong. Both the products I'll be writing in the back page. Let's see. So here, when we take an acid, okay, RCOH, and you're going to take PCl3, right? So you'll be getting RCOCl plus H3PO3. So here, this is the concept with PCl3. Suppose if it is PCl5, right, students, RCOCH plus PCl5, then the compound is RCOCl plus POCl3 plus HCl. So 3 plus 1 4, 4 plus 1 5, right? So these are the reactions. Sorry for the inconvenience. These two reactions take out. It did not learn wrong. So this is the acid chemical reactions of acids, right? So as I said, I'll meet you again with the next topic, that is name reactions of carbonyl compounds. I'll be taking 2 pages, and after that I'll be teaching you the name reactions of carboxylic acids, and then I'll finish off with the structure of carboxylic acid as well as carbonyl group in my next video. Thank you for watching. Stay connected. This is Vani ma'am signing off, and I'll meet you again with the next video. That is the name reactions.